Hello there, and welcome to Science for Sleep, where curiosity drifts softly through the stars and science takes the scenic route towards slumber. Tonight, we're gazing upward, not in search of answers exactly, but in quiet wonder, because somewhere above you, scattered across the dark like glowing grains of sand, are hundreds of billions of stars, and around many of them, unseen, unknown, are worlds. Whole planets circling in silence, each one with its own story written in gravity and light. Some are small and rocky, some are vast and gaseous, some are searing hot, others frozen and still. But among them, a question flickers, one that has followed us for centuries, whispered between dreamers and telescopes alike. How many of these distant worlds could be alive? It's an innocent kind of question, the sort that grows in the quiet hours, not demanding, just wondering. Maybe you've looked up at the night sky before and felt that tiny tug, that almost childlike thought. Could someone, somewhere, be looking back? Maybe not with eyes like ours, maybe not breathing our kind of air, but existing nonetheless. Aware, curious, maybe even wondering the same thing. You can almost imagine it, can't you? Somewhere, far beyond the haze of our own atmosphere, another small being on another small planet, gazing up at their own sky and feeling the same small ache of curiosity. Before we begin our long, slow drift through the galaxy tonight, I'd love to know where you're listening from. What corner of the Earth you calling home? Maybe it's morning and sunlight is pouring in softly through your window. Maybe it's night and the stars outside your city glow faintly behind clouds. Wherever you are, you and I are both floating in the same Milky Way, a vast spiralling city of stars that holds every sunrise and every moon we've ever known. It's humbling, isn't it, to think that this calm, sleepy conversation is taking place on one small world among hundreds of billions. And yet, somehow, here we are, sharing a moment, sharing a question. If this gentle journey through the cosmos helps you find a little peace, or if the sound of science told softly brings you comfort as you drift towards sleep, it would mean a lot if you left a like or subscribed. Not just for me, but because every quiet voice that joins this little constellation of listeners helps it glow a little brighter. A calm community, scattered across time zones and cities, finding stillness together beneath the same stars. So get comfortable. Let the day fade behind you like a sunset seen from the window of a slow-moving train. Take a breath. Let your shoulders loosen, your jaw soften, and your mind wander toward the night sky. Because tonight, we're not just counting stars, we're counting possibilities. We're exploring what it means to ask, not how vast the universe is, but how welcoming it might be. When you think about it, the Milky Way itself is almost too large to picture. Our minds are built for mountains and oceans, not galaxies. Even the word billion tends to slip past our understanding. Yet here we are, living inside a spiral of about 400 billion stars, maybe more. That's 400 billion suns, each one surrounded by its own realm of orbiting worlds. If even a small fraction of those stars host planets, and if even a smaller fraction of those planets have the right conditions for life, then we're talking about millions, perhaps billions, of potential homes scattered through the dark. It's a dizzying number, but it's also oddly soothing, like realizing that the universe is big enough to hold every dream we've ever had. Astronomers used to think our solar system was something special, that planets were rare, precious, unique. For centuries, the only ones we knew of were our own, the small family orbiting our sun. But as our telescopes grew sharper, the universe began to reveal its secrets. In the last few decades, we've discovered thousands of exoplanets, worlds orbiting stars far beyond our own. Some are massive and stormy like Jupiter, some are small and rocky like Earth, some are tidally locked, showing one face forever to their sun, while others dance in intricate orbits, tugging and swaying with their neighbours in gravitational ballet. And every time a new one is found, it adds another possibility to the quiet question we began with. Could life exist there? Could someone live under that sky? The methods used to find these worlds are almost poetic in their patience. Imagine staring at a distant star for months, waiting for the faintest dip in its brightness, a tiny flicker that lasts only a few hours. That dimming might mean a planet has passed in front of it, blocking just a fraction of the light. From that single flicker, scientists can calculate the planet's size, its orbit, even the composition of its atmosphere. A whole world revealed by the softest shadow. There's something deeply human about that kind of discovery. The ability to find meaning in subtlety, to read entire worlds from a few stolen photons. But before we start counting habitable planets, it helps to step back and ask what habitable really means. It doesn't just mean a place that looks like Earth. It means a place where conditions might allow life to survive, even if that life is nothing like us. Somewhere with energy, chemistry and time, the ingredients that together seem to spark complexity from chaos. And in that sense, habitability is less about geography and more about opportunity. It's about the chance for nature to try something new. When we talk about habitable planets, we often start with the idea of the habitable zone, sometimes called the Goldilocks zone. Not too hot, not too cold, just right. It's the distance from a star where liquid water could exist on a planet's surface, not frozen solid or boiled away. On Earth, water is life's gentle accomplice. It carries nutrients, shapes landscapes, and flows through every living cell. So when astronomers look for signs of habitability, they look for water first. But even that is only the beginning. A planet might be the right distance from its star and still be lifeless if its atmosphere is too thin, too thick, too toxic, or too unstable. It might be perfectly placed, but locked in perpetual darkness or battered by radiation. The universe has a way of mixing generosity with challenge. And yet, we keep finding worlds that make us hopeful. Some orbit stars much smaller than the Sun, glowing red and cool. These stars, called red dwarfs, are the most common kind in the galaxy. They burn slowly and live for trillions of years, giving any planets around them more than enough time to evolve. Astronomers have found that many red dwarfs host Earth-sized planets, right in their habitable zones. Planets like Proxima b, just 4 light-years away, practically next door in cosmic terms. It circles its star every 11 days, close enough to feel its warmth, but not so close as to burn. We don't yet know if it has an atmosphere or water, but even the possibility is enough to make you pause. Just 4 light-years. It sounds small until you remember that 1 light-year is nearly 6 trillion miles. Still, it's close enough that we can imagine it, maybe even reach it someday, if we're patient enough. Then there are systems like TRAPPIST-1, where 7 Earth-sized planets orbit a tiny star about 40 light-years away. 3 of them lie in the habitable zone, meaning they could have liquid water. Imagine that, a single system with multiple potentially habitable worlds, like a miniature version of our own solar system but more densely packed, more intimate, like marbles around a candle flame. When astronomers first announced the discovery, it felt like the universe had suddenly revealed a family portrait, a reminder that Earth is not an only child but part of a larger cosmic lineage. Still, it's worth remembering that habitable doesn't mean inhabited. We haven't yet found life anywhere beyond Earth. Every planet we've discovered so far is, as far as we know, empty, silent, waiting, mysterious. But absence of evidence isn't evidence of absence, as the saying goes. Life is stubborn. It thrives in boiling vents, frozen tundra, acidic lakes, radioactive ruins. It adapts to pressure, heat, cold, and darkness. If Earth has taught us anything, it's that life doesn't need perfection. It just needs a chance. Sometimes, when you think about all those chances scattered across the galaxy, it's almost too much to take in. Each star is a coin toss, each planet a potential spark. Multiply that by hundreds of billions, and the odds begin to feel almost inevitable. Not inevitable in the sense that life must exist elsewhere, but inevitable in the sense that the universe seems too fertile, too creative, to have made only one garden. And maybe that's the real wonder. Not that we're alone, but that we're even asking the question. If you were to look at the Milky Way from far above, you'd see a great spiral of light stretching about 100,000 light-years across. In its swirling arms are clusters of stars, clouds of dust, and lanes of glowing gas, the raw materials of worlds. Somewhere near one of those arms, about halfway from the centre to the edge, lies our Sun, quietly orbiting like a single grain of sand in a galactic dune. Around it, 8 known planets, dozens of moons, countless asteroids and comets, all bound together by gravity's gentle pull. It's a modest neighbourhood in a vast city of stars, but it's home. And if we can find life here, on a small rock orbiting an ordinary star, then surely it's not the only address with a beating heart. When scientists estimate how many habitable planets there might be in the Milky Way, they start with the stars themselves. There are about 400 billion of them, give or take a few hundred billion. Not all are suitable hosts. Some are too massive, burning out too quickly. Others are too dim or unstable, but roughly half of them, maybe more, are thought to have planets, and of those perhaps 1 in 5 might have an Earth-sized planet in the habitable zone. If you do the math, even conservatively, that means there could be tens of billions of potentially habitable planets in our galaxy alone. Tens of billions of Earth-like worlds, each with its own oceans, mountains, skies and mysteries. Of course, Earth-like can mean many things. Some might be desert worlds with thin air and shallow seas. Others could be water worlds with no land at all, just endless sunlit waves. Some might be covered in clouds, their surfaces hidden forever from view. But if even a small fraction of them harbour life, even simple life, then the galaxy is not just a collection of rocks and stars, it's a living mosaic, humming quietly in the background of the universe. It's humbling to think that all of this began with a question, asked by people looking up at the same stars we see tonight. Long before telescopes, before rockets, before satellites, there were people lying on their backs in fields, watching the constellations drift overhead, and wondering if the lights were other suns, wondering if there were others looking back. That same wonder has never left us. It's woven into our curiosity, into every mission we launch, every signal we listen for. The search for habitable worlds is also the search for ourselves, for understanding what it means to be alive in a universe that may be full of life. As you listen, the Earth keeps turning, the stars keep burning, and somewhere, light from distant worlds travels through the dark, carrying secrets we haven't yet learned to read. It will take years, decades, centuries maybe, before we know just how many of those worlds could cradle life. But the fact that we can ask, that we can build machines delicate enough to measure the shadow of a planet 100 light-years away, feels like a kind of life in itself, a testament to our need to reach out, to connect, to know. So as the night deepens around you, let that question linger a little longer. How many worlds out there might be like ours? How many oceans are shimmering under alien moons? How many skies are tinted with unfamiliar colours, filled with sounds we've never heard? And how many eyes, or something like eyes, are looking out from those worlds, feeling the same quiet curiosity we feel now? Maybe the answer is far away. Maybe it's impossibly close. Maybe it's waiting on a signal we haven't yet recognised. Or maybe the universe doesn't rush to reveal its secrets. Maybe it waits for us to listen more softly, to look more gently. Because sometimes the most extraordinary discoveries begin not with an explosion of revelation, but with a whisper, a soft wondering in the stillness of night. When you look up at the night sky, it can be easy to forget just how much of it there is. The darkness feels endless, but what you're really seeing isn't empty space. It's distance, it's depth, a kind of cosmic ocean stretching so far that even light, the fastest thing we know, takes thousands of years to cross it. Each tiny point of light is a wave crest, a small ripple of brightness from something unimaginably far away. And just as the ocean on Earth hides its islands beneath miles of water, the ocean above us hides its worlds beneath miles of darkness. We often describe the Milky Way as a galaxy, but that word feels too simple, too neat for something so vast. It's a spiral of hundreds of billions of stars, each one a sun in its own right, surrounded by dust, gas, and invisible halos of dark matter that we can't quite see but know are there. When you step outside on a clear night and notice that faint milky band stretching across the sky, you're looking edge-on into our galaxy's disk. The glowing path of starlight from millions of suns blending together. It's hard to grasp that you're part of it, drifting inside it, orbiting quietly within this luminous whirlpool of matter and time. If you were floating far beyond the Milky Way and could see it from a distance, it would look like a great pinwheel suspended in the dark, its arms curling gracefully around a bright centre. Those arms are full of stars, not evenly spread but gathered in clusters and clouds, some young and blue and fierce, others old and dim, burning their last fuel in quiet defiance. Our sun sits in one of these arms, a little off-centre, not in the crowded core but out toward the calm edges, where things are stable enough for life to take its time. It's the galactic equivalent of living by the sea, not too close to the city, not too far from the shore. When astronomers describe the Milky Way, they often talk about its components: the bulge, the disk, the halo. The bulge is the dense, bright centre where stars cluster tightly, orbiting a supermassive black hole called Sagittarius A. The disk is the broad plain where most of the galaxy's stars and planets reside, including us. The halo surrounds it all, a vast, faint sphere of ancient stars and mysterious matter extending far beyond what we can see. But when you strip away the technical language, what remains is something simple and beautiful. The Milky Way is not just a structure, it's a habitat, a place where stars are born, live, and die. A place where worlds can form, where chemistry can take root, and where the possibility of life might quietly unfold. When you picture the galaxy as an ocean, the stars become islands scattered through an enormous sea, each one with its own shores, its own weather, its own inhabitants, or perhaps none at all. To cross from one to another would take longer than any human lifetime, longer than any civilization has ever lasted. Even the nearest star to us, Proxima Centauri, is more than 4 light-years away. That's about 25 trillion miles. If you could travel as fast as a commercial airplane, it would take you over 50 million years to get there. The numbers quickly lose meaning, but they remind us that our home, Earth, is not just small. It's a speck adrift in a cosmic tide. Yet that same smallness has a kind of grace to it, because despite the scale, we can still measure, observe, and imagine. We can send telescopes into orbit to stare at distant stars and read the tiny flickers of light that tell us a planet might be there. We can launch spacecraft that drift to the edge of the solar system, still whispering back faint signals after decades in the dark. We can map the positions of stars across the galaxy with such precision that we can almost see the Milky Way breathing. Stars moving, drifting, orbiting together like currents in an invisible sea. And somewhere among all of that, we can ask a simple question. How many of those distant islands might be safe for life? It's a strange thing to wonder about something so far away, yet we do it constantly. Because even though we can't visit them, we can still sense their presence. The Kepler Space Telescope, for example, spent years staring at a patch of sky no larger than the width of your hand held at arm's length. In that tiny sliver, it found thousands of planets. Thousands. And if that many exist in one narrow slice of the sky, then across the entire galaxy there must be billions more. Billions of planets orbiting billions of suns like bubbles in a vast cosmic tide. Astronomers often say that planets are the rule, not the exception. For every star you see, There are likely at least one or two worlds orbiting it. Many stars probably have entire systems, families of planets, moons and asteroids bound together by gravity. It's not hard to see the pattern. The galaxy forms stars from clouds of dust and gas. Around those newborn stars, leftover material flattens into disks. Inside those disks, grains of rock and ice collide, stick together and grow. Over millions of years, they become planets. It's a natural process, one that seems to happen wherever stars are born. And because stars are born everywhere, the creation of planets is not a rare event. It's a constant one. If you could stand somewhere high above the Milky Way and look down, you'd see a living map of creation. Bright patches where stars are forming, dark regions where dust clouds hide potential new systems, and shimmering fields of older stars already surrounded by their planetary families. Every one of those systems is like a drop of water in the galactic ocean, separate yet part of the same grand pattern. Our own solar system is just one of those drops, and even within it, life has shown an impressive ability to adapt. On Earth, we find organisms living miles underground, in boiling springs, in frozen deserts, in the crushing depths of the ocean. Life has filled every corner that physics allows. It's hard not to imagine that the same thing could be happening elsewhere, hidden under alien skies. Scientists sometimes describe habitability as a delicate balance. A planet needs the right temperature, atmosphere and chemical ingredients. But when you look at how resourceful life can be, that balance starts to look more like a range, a broad, forgiving range that allows for many variations. Maybe life doesn't need a planet just like ours. Maybe it could thrive under red suns, in icy shells, or in atmospheres rich with gases we would find deadly. The ocean above us could be full of experiments, each world a new attempt at the same ancient trick, turning chemistry into biology. There's something deeply calming about that idea. The thought that nature keeps trying, endlessly, patiently, across billions of years and billions of miles. It doesn't hurry. It doesn't demand success. It simply continues, like waves repeating themselves on a distant shore. The Milky Way, in that sense, isn't a static structure. It's a story in motion. Stars form in clusters, drift apart and die in brilliant explosions that scatter elements into space. Those elements, carbon, oxygen, nitrogen, iron, become the building blocks of new stars, new planets, and perhaps new forms of life. The galaxy recycles itself constantly. Every atom in your body was forged in a star that lived and died long before the Earth existed. When you breathe, you're recycling stardust. When you look up, you're looking at your own history spread across the sky. And yet, for all our scientific progress, we've only begun to explore the edges of that ocean. Our most powerful telescopes can detect exoplanets orbiting nearby stars, but even the closest ones are beyond our reach. Light from those worlds takes years to arrive, and for now our ships crawl slowly compared to the distances involved. Still, the data we gather tells us enough to dream responsibly. We know that some planets are rocky, some have atmospheres, some even show hints of clouds. We can model their climates, estimate their temperatures, and predict whether liquid water could exist there. Every discovery adds another drop to the ocean of possibility. Some of these worlds orbit stars much smaller and cooler than the Sun. They glow dimly, casting red light on their planets' surfaces. To us, such light might look eerie, but for any organisms living there, if there are any, it would be normal, the colour of home. Imagine a world bathed in perpetual crimson twilight, where photosynthesis might use infrared light instead of visible light, and plants, if they exist, might not be green at all but deep black or shimmering silver to capture every photon. Other planets orbit hotter stars, their skies pale blue and bright, their days shorter, their seasons unstable. Life there, if it evolved, would face challenges we can barely imagine. Intense radiation, rapid weather changes, short lifespans for their suns. But perhaps life would adapt differently, evolving protective shells, underground colonies, or entirely new ways of storing energy. The diversity of environments across the galaxy suggests that if life exists elsewhere, it could look unimaginably different from anything we know. It's humbling to think that all of this unfolds in silence. Space has no sound, only light. The galaxy spins, stars are born and die, planets orbit faithfully, and yet from where we stand, it's all perfectly quiet. That silence isn't emptiness. It's the hum of distance, the pause between cosmic notes. And in that pause, we find room to wonder. The ocean above us has tides too, though they move on scales of millions of years. Stars drift slowly through the galaxy, changing neighborhoods as they orbit the center. Our sun, for instance, travels around the Milky Way once every 230 million years. During that journey, it passes through different regions, denser arms full of young stars, quieter stretches of interstellar space, and perhaps even clouds of dust that dim the starlight reaching Earth. Every part of that journey subtly changes our environment. Over long enough timescales, it could influence Earth's climate, the formation of comets, even the history of life itself. The galaxy isn't just a backdrop, it's a participant in our story. When you think of it that way, habitability becomes something larger than just a planet's position or atmosphere. It becomes a relationship between a world and its galaxy. Where a star lives, how stable its orbit is, how often it encounters cosmic hazards, all of these factors matter. The Milky Way is not uniform. Some regions are violent, full of radiation and stellar explosions. Others are calm and nurturing. Our solar system, it turns out, resides in one of the quieter suburbs, a good place to grow life without too many interruptions. You could almost call it a cosmic coincidence, though perhaps it's better described as cosmic luck. And still, even with all that luck, the ocean above us remains mostly unknown. We've mapped only a fraction of it. We've sent out probes that will one day drift between the stars, but they won't reach another system for tens of thousands of years. For now, we rely on light, on the patient collection of data from telescopes scattered across Earth and orbiting high above it. Each photon captured tells us a little more about the seas of stars we float in. If you were to lie back now, close your eyes, and imagine the galaxy not as a map but as a feeling, what would it be like? Maybe it's not cold or distant at all. Maybe it feels like the ocean at night, vast, calm, softly luminous, stretching far beyond sight but always there, wrapping around you quietly. You're not outside of it, not apart from it. You're swimming in it. Every atom, every breath, every heartbeat is part of its slow, endless motion. The ocean above us doesn't rush. It doesn't worry about whether life exists on 100 worlds or 1,000,000. It simply holds them all, letting time and gravity do their work. And within that stillness, somewhere, life might be beginning again, a few molecules finding each other, a fragile spark repeating a pattern that started billions of years ago here, on this small blue world. If you've ever tried to count the stars on a clear night, you probably gave up long before you finished. There are too many, too bright, too distant, and yet too faint all at once. Your eyes can take in a few thousand from the darkest skies on Earth, but that's only the thinnest layer of what's really there. The rest, hundreds of billions, remain invisible, hidden behind clouds of dust or simply too far away for our eyes to reach. Counting them is a little like trying to count waves on the ocean. You can measure the rhythm, the shape, even the swell, but the number always slips through your fingers. Still, humanity keeps trying, because somewhere inside that counting lies the hope of understanding just how vast, how generous this galaxy truly is. Astronomers, of course, have better tools than the naked eye. But before there were telescopes, there was patience and imagination. People once charted the heavens by hand night after night, mapping the positions of stars with quills and ink. They named constellations, not to measure the universe, but to make sense of it, to tell stories across generations. Those stories were the first maps, Orion chasing the Pleiades, Cassiopeia waiting in her chair, the Milky Way imagined as the spilled milk of a god, or the path of migrating souls. We have always needed to describe what we see, even when we don't understand it. When Galileo turned his telescope to the sky in the early 1600s, he discovered that the Milky Way wasn't a glowing cloud at all, but a river of countless stars. That moment marked the beginning of astronomy as we know it, the shift from seeing the sky as myth to seeing it as measurement. But even Galileo could not have imagined the scale we know today. His small telescope revealed perhaps a few thousand additional stars, a shimmering veil of light that hinted at infinity. He wrote that the universe seemed full of innumerable stars, and he was right, though even he underestimated just how innumerable that would turn out to be. To count the stars in the Milky Way, scientists rely on models, not lists. They can't tally them one by one, so they estimate based on the light the galaxy gives off, its mass and its shape. Each method offers a different perspective, a different kind of candlelight by which to measure the darkness. One approach involves studying how stars move, how their collective gravity tugs on the galaxy's spiral arms. From those motions, astronomers can infer how much mass is hidden within. Another method measures the total brightness of the Milky Way and compares it to known luminosities of individual stars. Still another uses population synthesis, a kind of statistical approach that estimates how many small, dim stars must exist to explain the galaxy's observed glow. No matter which path they take, the answer tends to hover somewhere between 100 billion and 400 billion stars. The range is wide, but that's because the galaxy itself is uneven, full of regions we can't see directly. Some stars are obscured by dust lanes that absorb visible light, while others are faint red dwarfs too dim to detect from great distances. The irony is that the most common stars in the Milky Way, those small red ones, are also the hardest to see. There could be hundreds of billions of them quietly shining, each with its own family of planets, each invisible to all but the most sensitive instruments. Imagine standing in a dark field at night, holding a single candle. The flame gives off a warm, fragile glow, just enough to see the air shimmer around it. Now imagine you're surrounded by candles stretching to the horizon, some close enough to feel their heat, others so far away their light barely reaches you. That's roughly what it's like to live inside the Milky Way. Each star is a candle in the dark, its light overlapping with billions of others, creating the faint, diffuse glow that washes across the sky. When you look up, you're not seeing a single brightness, but the combined light of countless tiny flames. Counting them by candlelight isn't just poetic, it's literal. Even now, with space telescopes and advanced computers, we still depend on approximation. The European Space Agency's Gaia mission, launched in 2013, has mapped more than 1 billion stars in unprecedented detail. Each one's position, brightness, motion, and colour have been recorded, creating a three-dimensional map of our corner of the galaxy. 1 billion might sound like a lot until you remember it's only a small fraction, maybe 1% of the total. Yet that 1% has revolutionised our understanding of the Milky Way structure. We can now trace how stars move through the galactic disk, how clusters dissolve, how new generations form from the ashes of the old. The picture grows sharper with every year, but it's still only a glimpse. The full ocean remains beyond reach, too vast to capture all at once. There's a certain humility that comes with this kind of counting. The numbers are immense, but they don't make us smaller. They remind us how rare it is to be aware of them at all. A brain made of carbon and calcium, sitting on a planet made of rock and water, has managed to measure the structure of a galaxy made of stars and dust. It's not just science, it's participation. We are part of the system we study, built from the same matter, observing itself. Each star we count tells a story of time. Some are ancient, born when the universe was young, their light crossing tens of thousands of years before reaching us. Others are newborn, still surrounded by swirling disks of gas where new planets are taking shape. The Milky Way is about 13 billion years old, give or take, and stars have been forming within it for most of that history. In any given moment somewhere in the galaxy, a new star ignites while another fades out. The population is always changing, always renewing itself like waves in an endless sea. It's tempting to think of the Milky Way as static, a beautiful frozen spiral hanging in space, but in reality, it's alive with motion. Every star, including our Sun, is moving through it, orbiting the galactic centre. The Sun travels at about 200 kilometres per second, completing one orbit every 230 million years. That means since the Earth formed, our solar system has circled the galaxy more than 20 times. Each revolution carries us through new regions, new star fields, new clouds of gas and dust. If you could speed up time and watch the galaxy spin, it would look like a living organism, its arms flexing, its stars pulsing like cells in a vast body. Counting the stars, then, isn't just about quantity. It's about rhythm, understanding how they move, how they form and how they fade. The Milky Way's disk is about 100,000 light-years wide, but only 1,000 light-years thick. Within that thin layer, stars orbit in nearly circular paths, weaving around each other with quiet precision. The balance is delicate but stable, like a flock of birds moving as one. Over billions of years, gravity keeps the pattern together, even as individual stars drift slightly up or down, creating ripples that travel through the disk like waves in water. Those waves can trigger new bursts of star formation, compressing gas clouds until they collapse under their own weight. Every generation of stars changes the galaxy a little more. Massive stars live fast and die young, exploding as supernovae that scatter heavy elements into space. Those elements, carbon, oxygen, iron, and all the rest, become part of the next generation of stars and planets. In that way, the act of counting stars is also an act of tracing ancestry. You could follow the chain backward, from our Sun to earlier stars that forged its materials, to still earlier ones that formed in the galaxy's youth. Eventually you'd reach the first stars, born from pure hydrogen and helium, lighting up a universe that had only just begun to shine. For all our instruments, though, the most profound tool we have for understanding the galaxy might still be perspective. Numbers help us quantify, but imagination helps us feel. It's one thing to know that there are hundreds of billions of stars. It's another to imagine what that really means. Suppose you tried to count them aloud, one per second, without stopping. Even if you lived for a century, you wouldn't finish. You'd need millions of lifetimes to name them all. The galaxy's scale defies our sense of time as much as it does our sense of size. And yet, despite that, every discovery brings the distant a little closer. When astronomers find a new star with planets, they're not just adding another data point. They're expanding the map of where life could exist. Each system is a potential story, a place where chemistry might have found a foothold, where oceans might ripple under alien skies. The act of counting becomes a kind of hope. Every star catalogued is another candle lit against the dark, another reminder that the universe might be full of homes we haven't met yet. There's also a practical reason for all this measuring. To understand how many planets might be habitable, we need to know how many stars there are, what kinds they are, and how long they live. Stars come in a wide range of masses and temperatures, from the small, cool red dwarfs to the enormous blue giants. The smaller ones burn their fuel slowly and can live for trillions of years, giving any nearby planets immense stretches of time to evolve life. The large ones burn hot and fast, lasting only a few million years before collapsing or exploding. Habitable planets are more likely to orbit the steady middleweights, stars like our Sun, with lifespans long enough to offer stability, but not so dim that their planets freeze in darkness. When scientists model the Milky Way, they include these differences. They calculate the proportions of each type of star, the fraction that might host planets, and the fraction of those planets that fall into their stars' habitable zones. From those probabilities, they estimate how many worlds might be capable of supporting life. It's not an exact science, but it's an informed guess built on layers of observation. The more we learn about stars, the sharper those guesses become. The night sky you see tonight is already a kind of time machine. Some of the stars visible now may no longer exist. Their light has been travelling for centuries or millennia to reach us. When you gaze at them, you're seeing history, ancient light crossing the cosmic sea. It's one of the quiet miracles of astronomy, this ability to look backward through time simply by looking up. The galaxy's light is a record of everything it's ever been. Counting its stars is like reading its diary, one entry at a time. And yet, for all our efforts to measure and map, the Milky Way remains an intimate mystery. You can know that it contains hundreds of billions of stars and still, on a quiet night, feel that it was made just for you. That intimacy isn't arrogance, it's perspective. Every creature that has ever looked up has seen the same stars from their own small patch of ground and wondered what they mean. Every observation, every calculation, every candle held against the dark is part of the same ongoing act of curiosity. It's almost funny to think that the very tools we use to study the universe, telescopes, computers, equations, are themselves made from the materials of old stars. The glass in a telescope's lens, the silicon in a circuit, the iron in a mount, all were forged in stellar furnaces long before humans existed. In a literal sense, the galaxy is studying itself. The light from one star travels across the void and lands on an instrument built from the ashes of another. That connection might not make the numbers smaller, but it does make them warmer. So here we are, counting by candlelight. Not because we expect to finish, but because the act itself has meaning. Every new star catalogued brings us closer to understanding how many worlds might exist, and how many of those worlds could be gentle enough, stable enough, or lucky enough to host life. The numbers are vast, but they're not impersonal. They form a bridge between us and the unknown, a way of turning distance into belonging. The ocean above us isn't something separate. It's something we're inside of, something we participate in. Every measurement, every flicker of light, every orbit plotted is a note in a larger harmony. And as we continue to count, patiently, carefully, we begin to notice patterns, places where stars gather more densely, regions where planets seem more likely to form, currents in the galactic sea that may guide the creation of new worlds. We're still near the beginning of that understanding, still measuring by the glow of a small flame in a vast night. But that small flame is enough. It's how all discoveries begin. A bit of light, a bit of wonder, and the quiet belief that what we find, no matter how far away, is part of us too. When we look out at the night sky and think about all those stars, it's natural to wonder how many of them might have planets like ours. Worlds that could hold air and oceans, mountains and clouds, weather and seasons, maybe even something alive, moving beneath alien skies. For most of human history, that question lived only in imagination. We could see the stars, but we had no way of knowing if any of them had company. Our telescopes showed light, not motion, and even the closest stars were impossibly far away. For centuries, Earth seemed to stand alone in a vast silent universe. That silence was never comfortable. People filled it with stories, with gods and spirits, with endless possibilities of invisible worlds. Some ancient philosophers suggested that other Earths must exist, scattered among the stars. Others dismissed the idea as arrogance. How could there be anything else like us? The argument lingered for thousands of years, shifting with each new discovery until technology finally caught up with curiosity. The modern search for other Earths began quietly, not with grand telescopes or futuristic spacecraft, but with a simple question and a great deal of patience. How do you find something you can't see? A planet doesn't shine on its own. It reflects the light of its star, and that light is faint compared to the brilliance beside it. It's a bit like trying to spot a firefly next to a lighthouse from thousands of miles away. The light of the star overwhelms everything else, drowning its planets in glare. For a long time, that problem seemed unsolvable. Then scientists realized that while a planet might be invisible, its presence could still be felt. Every planet, no matter how small, exerts a gravitational pull on its star. That pull makes the star wobble ever so slightly as the planet orbits around it. The movement is minuscule, a shift in position of just a few meters per second, but with precise instruments, it can be detected. This is called the radial velocity method, and it became one of the first ways we found planets around other stars. By studying the tiny wobbles in a star's light, scientists could infer the presence of an unseen companion tugging on it in a steady rhythm. The first confirmed discovery came in 1995, when astronomers Michel Mayor and Didier Queloz announced that they had found a planet orbiting a star called 51 Pegasi, about 50 light-years away. The planet was nothing like Earth. It was a gas giant larger than Jupiter, orbiting so close to its star that a year there lasted only 4 days. It was blisteringly hot, a world of roaring winds and glowing skies, but it was proof. Planets did exist beyond our solar system. The night sky had changed forever. That discovery opened a floodgate. Within a few years, dozens of exoplanets were found, then hundreds, and eventually thousands. New techniques joined the search, each one refining the view. The most transformative of all was the transit method, the quiet art of watching a star and waiting for it to dim. When a planet passes directly between its star and our line of sight, it blocks a tiny fraction of the light. The dip might last only a few hours and dim the star's brightness by less than 1%, but that small shadow can reveal a great deal. From it, scientists can determine the planet's size, its orbital period, and with additional measurements, even hints about its atmosphere. This method works best when observed continuously, which is why space telescopes have become so crucial. Freed from the distortions of Earth's atmosphere, they can stare at a single patch of sky for months or years without blinking. The Kepler Space Telescope, launched in 2009, was built for exactly this purpose. For nearly a decade, it monitored over 150,000 stars, patiently waiting for those tiny dips in brightness. Each dip, each flicker, was a potential world. By the time Kepler's mission ended, it had discovered more than 2,600 confirmed exoplanets, with thousands more candidates awaiting verification. Among them were worlds strikingly similar to Earth, small, rocky, orbiting in the temperate zones of their stars. For the first time, we could look at data and say, with some confidence, that planets like ours are common. Not rare, not exceptional, but part of the ordinary fabric of the galaxy. That realization changed the question from do other Earths exist to how many of them are out there. Each planet found by Kepler was just a number in a vast catalogue, but behind every number lay a story. Some orbited single suns, others circled double stars like the fictional world of Tatooine. Some were so close to their stars that their surfaces likely melted. Others drifted on wide, cold orbits where sunlight was little more than a distant glow. Each system offered a new variation on a theme: gravity, light and matter, playing endless combinations of possibility. One of the most remarkable discoveries came from a small, cool star about 40 light-years away called TRAPPIST-1. Observations revealed not just one planet, but 7, all roughly Earth-sized, all orbiting close to their parent star. 3 of them sit in the so-called habitable zone, where temperatures could allow liquid water to exist. It's a system so compact that all 7 planets would fit comfortably within Mercury's orbit around the Sun, their skies likely filled with each other's silhouettes. The idea that such a miniature solar system could host multiple habitable worlds made astronomers rethink what was possible. Then came Proxima Centauri b, discovered in 2016, a planet orbiting the nearest star to the Sun. Just over 4 light-years away, it's the closest potentially habitable world we know of. Its star, a dim red dwarf, shines faintly in the constellation Centaurus, invisible without a telescope, but there, circling quietly, might be a world not so different from ours. The thought that the nearest star could have its own Earth-like planet feels both astonishing and strangely inevitable, as if the universe has been waiting for us to notice. The search, though, is not just about numbers or proximity, it's about detail. Once a planet is found, the next step is to learn what it's like, its temperature, its atmosphere, its potential for life. That's where things become even more delicate. By studying the starlight that filters through a planet's atmosphere during a transit, scientists can detect traces of gases, certain combinations, oxygen, methane, water vapour, carbon dioxide, can hint at biological activity. It's like analysing the faintest fingerprints left on a beam of light. So far, none of the known exoplanets show definitive signs of life, but the techniques are improving quickly. The upcoming generations of telescopes, like the James Webb Space Telescope and others that will follow, are designed to look deeper and more precisely, able to detect the chemical breath of distant worlds. Each new discovery refines our sense of what's possible. Some planets are tidally locked, with one side in perpetual daylight and the other in endless night. At first, scientists assumed such worlds would be uninhabitable, their climates too extreme, but computer models suggest that with a thick enough atmosphere, heat could circulate evenly, creating a twilight zone where conditions might be just right for life. Others orbit red dwarfs that flare violently, blasting radiation into space, yet even there, some planets might find shelter under thick clouds or deep oceans. The more we learn, the more we realise that life could adapt to far more than we once imagined. The search for other Earths is a quiet one because it depends on patience and precision rather than spectacle. There's no dramatic signal, no sudden revelation. Just long stretches of observation, long nights of data analysis, and the occasional glimmer of possibility. It's science in its most contemplative form, watching, waiting, listening. When you think about the scale of it, the numbers are astonishing. Our galaxy contains hundreds of billions of stars, and if even a small fraction of them have Earth-sized planets in their habitable zones, there could be tens of billions of potentially habitable worlds in the Milky Way alone. That's billions of chances for oceans, for weather, for life. The sheer abundance turns what was once speculation into something close to certainty. It's not whether they exist, but which ones we'll find first. And yet, despite this abundance, there's something beautifully fragile about the search. Each planet found is a point of light in a sea of darkness, a reminder that we are still at the beginning. The instruments we use are sensitive enough to detect worlds dozens of light years away, but we can't yet visit them. We can't even see most of them directly, just their shadows, their whispers in starlight. We know they're there, but their details remain hidden, waiting for technology we haven't built yet. That waiting has a strange rhythm to it. Years pass between discoveries. Spacecraft take decades to reach even the edge of our own solar system. Astronomical time moves differently from human time, and yet we still keep pace in our own way. We keep building better telescopes, better detectors, better ways to listen. It's a slow conversation with the universe, one question at a time. There's also a subtle human element to this search, the way it mirrors our desire for connection. To look for other Earths is, in some sense, to look for ourselves. Each discovery invites the question of what life might be like elsewhere, but it also makes us reconsider our own world. The thinness of our atmosphere, the rarity of liquid water, the stability of our star, all the fragile conditions that make Earth livable suddenly seem extraordinary. The search for other Earths is as much a study of gratitude as it is of exploration, and it's not just scientists who participate in it. Amateur astronomers, students and enthusiasts all around the world contribute data, analyse light curves, and help confirm exoplanet candidates. Some of the most interesting discoveries have been made by people sitting at their home computers, sifting through data released by NASA and the European Space Agency. The act of searching has become communal, shared across time zones and continents, a global collaboration built on curiosity. Imagine that for a moment. Thousands of people scattered across the planet staring at data from stars hundreds of light years away, all looking for the same tiny dip in brightness. It's a form of collective wonder, one that transcends language or culture. The quiet search for other Earths is really a quiet reminder of how connected we already are. There's a tenderness to the work too. Astronomers often describe their discoveries with a sense of affection. They speak of planets as neighbours, of stars as hosts, of systems as families. Each new world discovered is welcomed like a distant relative finally found. They may never see it directly, may never know its colours or clouds, but they know it exists. And that existence alone changes something deep inside our understanding of what's possible. When we imagine those other Earths, we often picture familiar things: blue oceans, white clouds, green continents, but the truth is, they might look nothing like ours. Some could have skies tinted orange or violet, seas made of methane or ammonia, continents of crystal or ice. Life, if it exists there, might not resemble anything we know. But the details hardly matter. What matters is the possibility. The idea that life finds a way, that the universe keeps making room for it. The search continues quietly, with new missions already underway and more planned for the coming decades. The Transiting Exoplanet Survey Satellite, or TESS, is scanning nearly the entire sky, following in Kepler's footsteps but focusing on stars closer to home. The James Webb Space Telescope peers even deeper, studying the atmospheres of distant worlds in exquisite detail. And future missions will go further still, building instruments capable of directly imaging Earth-like planets and even detecting signs of life. Each of these efforts adds another candle to the darkness, another flicker of understanding in the vast ocean above us. The discoveries don't come with fireworks or fanfare. They arrive quietly, as lines in a research paper, as graphs of light, as soft confirmations that somewhere another world exists. And maybe that's fitting. The universe doesn't rush, and neither should we. When you think about it, the quiet search for other Earths isn't just about finding planets. It's about learning to listen carefully, to notice the small patterns in the noise, to find meaning in faint light. It's an exercise in patience, humility, and wonder, qualities that seem increasingly rare, but that science, at its best, still teaches us to keep. As you lie back and imagine the sky above you, filled with stars you'll never see up close, it's comforting to know that among them there are other worlds. Some might be warm and wet, some frozen and dim, some entirely alien, but they're there, orbiting quietly, unseen but real. The search will go on, as gentle and steady as the turning of the Earth itself. When we think about what makes a planet habitable, we usually start with temperature. It sounds simple enough, not too hot, not too cold, but just right. It's the kind of balance we recognise instantly because we live inside it. Earth orbits at the perfect distance from the sun for water to remain liquid, for clouds to form, for rain to fall. If we were a little closer, our oceans might have boiled away. A little farther, and they could have frozen solid. This narrow band of comfort, this sweet spot where life can thrive, is what scientists call the habitable zone, or more gently, the Goldilocks zone. It's a phrase that comes from an old story, one about a girl and 3 bears, each bowl of porridge too hot, too cold, or just right. The story feels childish at first, but in the quiet context of astronomy, it carries a kind of poetic precision. Because finding the Goldilocks zone isn't about perfection, it's about balance, the fragile equilibrium between warmth and cold that allows complexity to emerge. For every star in the galaxy, there's a different version of that zone. Big, bright stars burn fiercely, radiating heat across enormous distances. But they live fast and die young. Their habitable zones stretch far out, but only for a short time before those stars exhaust their fuel and fade or explode. Smaller stars burn cooler and dimmer, their habitable zones drawn in tight and close. Red dwarfs, the most common stars in the Milky Way, have habitable zones so near that their planets complete orbits in just a few days. Yet those zones last for trillions of years, far longer than the lifespan of our Sun. The trick is finding a star that offers both stability and time. Life, as far as we know, doesn't rush. It takes billions of years for chemistry to turn into biology, for single cells to become ecosystems, for intelligence to arise. A stable star provides the stage, but the distance of its habitable zone sets the scene. Too close and radiation scorches the planet. Too far and everything freezes. But in between, in that narrow band, something extraordinary can happen. Molecules meet, water flows, and life can begin to write its slow story. Our own Earth sits comfortably in this band, though comfortably might be an illusion. The balance is always precarious. Tiny changes in our orbit, in the tilt of our axis, or in the brightness of the sun could shift our climate drastically. In the deep past, Earth has frozen over completely, a snowball world wrapped in ice from pole to equator. At other times, it has been a greenhouse, sweltering under thick clouds and steaming seas. Yet each time it recovered, stabilized, adapted. That resilience might be the true secret of habitability. Not perfect stability, but the ability to bend and survive. To imagine the Goldilocks zone on other worlds, scientists start with what they know. They calculate how much energy a star emits, how much light a planet receives, and how that energy would interact with an atmosphere. They run simulations adjusting for different compositions, carbon dioxide, nitrogen, methane, water vapour, to see how the surface temperature might change. It's not an exact science, because planets are complicated. Their climates depend on rotation speed, geological activity, magnetic fields, and countless other factors. But even with all those uncertainties, the habitable zone gives us a place to start, a way to narrow the search. It's remarkable to think that such a simple concept, the right distance from a star, could be the difference between a barren rock and a living world. Mercury and Venus, for example, lie just inside the Sun's inner zone. Mercury is too small to hold an atmosphere. Its day side is hot enough to melt lead, its night side cold enough to freeze metal. Venus, though nearly Earth's twin in size, has become a furnace, its thick carbon dioxide atmosphere trapping heat until the surface glows with volcanic intensity. On the other side, Mars sits near the outer edge of the habitable zone. It once had rivers and lakes, perhaps even shallow seas, but as its atmosphere thinned, the water disappeared. Today it's a dry desert under a pink sky, still whispering of what once might have been. When we apply the same reasoning to other stars, the possibilities multiply. Around a small red dwarf, the Goldilocks zone might be so close that a planet's year lasts only a few days. Such a world would likely be tidally locked, one side forever facing its sun in endless daylight, the other forever dark. For a long time, scientists assumed this would make life impossible, but models now suggest otherwise. If a planet has an atmosphere thick enough to circulate heat, the twilight region between day and night could be temperate, a ring of eternal sunset, perhaps home to winds, clouds, and liquid water. It's strange to think that somewhere in the galaxy, an entire world might exist in perpetual dusk, its skies painted in the soft hues of a permanent evening. Maybe rivers flow there under red light. Maybe something stirs beneath the clouds, following its own slow rhythm, unaware that its warmth depends on such a delicate balance. The universe seems to favour balance, even if it achieves it in ways we don't expect. One of the most fascinating systems discovered so far, TRAPPIST-1, offers a glimpse of how common that balance might be. Its 7 Earth-sized planets orbit a dim red star so close that they all fit within a space smaller than Mercury's orbit. 3 of them lie in the habitable zone. They're so near each other that, from one planet's surface, the others might appear as enormous moons in the sky, glowing softly with reflected light. If any of those worlds hold liquid water, they could be miniature oases in the cool, dim light of their sun, and if life ever arose there, it might leap from one world to another, carried by rocks and dust in interplanetary exchanges. The idea that a single system could host multiple habitable planets isn't just science fiction anymore. It's a real, measured possibility. But habitability is more than temperature. It's also about chemistry and protection. A planet needs the right elements: carbon, nitrogen, oxygen, phosphorus, the ingredients for molecules that can build, replicate, and evolve. It needs an atmosphere thick enough to trap warmth, but not so thick that it suffocates. It needs a magnetic field to shield its surface from cosmic radiation, and it needs time, long stretches of calm in which life can take hold. When we look for habitable worlds, we're really looking for stability within motion, for places where the cosmic forces of destruction and creation find a temporary pause. And yet, for all our careful criteria, the universe seems full of exceptions. We've found moons in our own solar system that could be habitable despite being far outside the traditional Goldilocks zone. Europa, one of Jupiter's moons, and Enceladus, circling Saturn, both hide oceans beneath their icy crusts. Those oceans are kept liquid not by sunlight, but by tidal heating, the flexing and squeezing of the moon's interiors as they orbit their massive planets. It's a reminder that warmth can come from many sources. The Goldilocks zone might not just exist around stars, it might also exist underground, under ice, even in the dark spaces between worlds. That realization expands the idea of habitability far beyond its original bounds. When astronomers first defined the habitable zone, they imagined Earth-like planets orbiting sun-like stars. But nature doesn't seem to limit itself to that model. The galaxy may be filled with hidden habitats, places where chemistry and physics conspire to create the conditions for life in ways we haven't yet imagined. In a way, the Goldilocks zone is less about geography and more about possibility. It's a concept that bridges the known and the unknown, giving us a framework to start from while reminding us that the universe rarely stays within our definitions. Every time we discover a new kind of planet, lava worlds, ocean worlds, gas dwarfs, super-Earths, we have to stretch the boundaries of what we consider habitable. Some planets might have thick hydrogen atmospheres that trap heat efficiently, extending the habitable zone farther out than expected. Others might have reflective clouds that keep them cool, even when they're closer to their stars. The Goldilocks zone, in truth, is a moving target. Still, the idea endures because it offers a simple way to imagine where life could be. It gives us something to look for, a region of calm in the cosmic storm, where temperature and chemistry align just enough to let water flow and life begin. That image of a thin ring of possibility circling a star is both scientific and deeply human. It mirrors our own existence, living on a narrow edge between too much and too little, thriving in a small window of balance. When you step outside and feel the warmth of sunlight on your skin, you're feeling the effect of that perfect distance. The sun's energy has travelled 150 million kilometres through space, and it arrives with just the right intensity to nourish plants, drive weather and sustain life. That same light, if received a little more or a little less, could have written an entirely different story. In that sense, the Goldilocks zone isn't just an astronomical concept, it's a quiet miracle we live inside every day. And perhaps that's why the search for habitable worlds feels so personal. When astronomers look for Earth-like planets in other stars' Goldilocks zones, they're also retracing the conditions that make our own existence possible. They're looking for echoes of home, for patterns that say, you're not alone. And every time they find a planet that fits, even approximately, it feels like confirmation that the universe is fertile, that the rules of life aren't unique to us. Still, even within the Goldilocks zone, life might not appear easily. A planet could have the right temperature and still lack the spark of chemistry that sets things in motion. It could be smothered by volcanic gases, sterilized by radiation, or frozen beneath clouds that block its sun entirely. Habitability doesn't guarantee life, it simply opens the door. What steps through that door, if anything, remains one of the greatest mysteries in science. In the long arc of time, that mystery gives us a sense of patience. The universe has had nearly 14 billion years to work with, and life on Earth took almost 4 billion years to evolve from simple cells to complex beings capable of asking questions. If similar processes are unfolding elsewhere, they might be happening right now, slowly, quietly, beneath alien skies, in the comfort of their own Goldilocks zones. It's humbling to think that the same balance that sustains us could be playing out billions of times across the galaxy. Every star has its own version of just right. Every world dances to its own rhythm of light and distance, and in that cosmic dance there may be countless stages where life performs unseen, waiting for us to notice the faint glimmer of its presence. The Goldilocks zone reminds us that life depends on delicate conditions, but it also shows us how generous the universe can be. Out of all the combinations of distance, heat and time, the odds have aligned here, on this small planet, to create oceans, forests, laughter and thought. And if it could happen here, then perhaps it could happen elsewhere too, carried by the same laws, the same chemistry, the same quiet persistence. The more we learn about those distant zones of balance, the more we realise that life is not a rare accident, but a natural outcome of stability and time. The Goldilocks zone is not a place so much as a promise, that somewhere out there, under the light of another sun, another world might be cradling its own version of home. Not every planet is lucky enough to find itself in the gentle warmth of a Goldilocks zone. Most of them fall outside that fragile ring, drifting through conditions that seem too harsh for life as we know it. Some orbit so close to their stars that their surfaces glow red with heat, while others wander in the cold, dim outskirts of their systems, locked in endless winter. These are the worlds of fire and ice, places that test the boundaries of what a planet can be and what life, in theory, might endure. When astronomers began discovering exoplanets, many of the first were these extremes. The easiest ones to detect were the big, close-in planets, giants orbiting their stars so tightly that their years lasted only a few days. They were called hot Jupiters, a name that sounds almost contradictory but fits perfectly once you imagine them. Massive gas planets, larger than anything in our solar system, circling their stars at distances so small that their atmospheres are heated to thousands of degrees. On such worlds, clouds form not from water, but from metals and silicates. Winds blow at thousands of kilometers per hour, and rain might fall as molten iron. One of the first hot Jupiters discovered, 51 Pegasi b, orbits its star so closely that it completes a full revolution in just 4 Earth days. That means its year is shorter than our work week. The side facing its star is blasted by relentless light, reaching temperatures that would vaporize rock. Yet even in such inhospitable conditions, the planet's existence was a revelation. Before it was found, no one had imagined a world like it could exist. Theories of planetary formation were rewritten almost overnight. What seemed impossible turned out to be common. There are others even stranger. WASP 76b, for example, lies about 640 light-years away. It's tidally locked, which means one side always faces its star, bathed in perpetual day, while the other remains in eternal night. On the day side, temperatures soar above 2000 degrees Celsius, hot enough to vaporize iron. The iron rises into the atmosphere, drifts on high winds toward the cooler night side, and condenses back into droplets falling as the iron rain. It's a world where it literally rains metal. where the sky glows with heat and the landscape, if it exists at all, would shimmer with molten light. As violent as these planets sound, they remind us that the universe doesn't design for comfort. It creates in abundance without preference, filling space with every variation physics allows. For every world that might be mild and green, there are thousands that are not. Planets scorched, shattered, frozen, or adrift. And yet, even among those extremes, there's beauty. The kind of beauty that comes from scale and diversity, from knowing that nature explores every possibility. Far from the stars, at the other end of the spectrum, are the frozen worlds, planets and moons so distant that sunlight arrives as little more than a faint cold whisper. In our own solar system, Pluto sits in that deep freeze. Once called the 9th planet, now reclassified as a dwarf, it circles the Sun at an average distance of nearly 6 billion kilometres. Its surface is a mix of frozen nitrogen, methane and carbon monoxide, sculpted into mountains of ice harder than rock. When sunlight hits those frozen plains, they release thin wisps of gas, forming a delicate, transient atmosphere that collapses again when the long winter returns. And yet, even Pluto has activity. The New Horizons spacecraft, which flew past it in 2015, revealed evidence of glaciers, winds, and perhaps even cryovolcanoes, eruptions not of molten rock but of cold slurries of ice and gas. That was the first real proof that even frozen worlds could be dynamic, changing, alive in their own slow way. Go farther still, and you reach worlds that drift through the galaxy without stars at all. Rogue planets, untethered wanderers ejected from their systems during formation. These lonely orphans travel through darkness, their only heat coming from the residual energy left over from their birth. Some might have thick atmospheres trapping that warmth, keeping them dimly glowing in the void. Others might be frozen solid, silent and invisible. The idea that entire planets drift unseen between the stars is almost eerie, but it's also a reminder of how vast and varied the cosmos is. For every stable orbit there's an exile, a planet lost to interstellar space, continuing its quiet journey with no sunrise, no sunset, only night. Between these extremes lie countless gradations, warm worlds, cold worlds, stormy ones, still ones, each with its own set of conditions. Some planets orbit stars that flare unpredictably, their skies constantly flashing with bursts of radiation. Others move in elongated orbits, swinging close to their stars before arcing back into the cold. On such worlds, the seasons would be unimaginable. Scorching summers followed by decades of winter. Cycles of melting and freezing that could last centuries. The question scientists ask isn't whether these places could support life like ours, but whether life in some form could adapt to them. On Earth, we've found organisms that live in boiling springs, in frozen tundra, in the deepest ocean trenches, and in radioactive waste. There are microbes that survive being frozen for decades, others that thrive in acid, salt, or near-total dryness. If life can exist in such extremes here, it might find a way elsewhere too. A planet of fire might harbour life underground, shielded from the heat. A world of ice might conceal a warm ocean beneath its crust. The universe doesn't lack imagination. Even within our own neighbourhood, we see examples of how extremes can hide potential. Europa, a moon of Jupiter, is a frozen sphere of ice. But beneath that ice lies an ocean larger than all of Earth's combined. It's kept liquid by the tidal flexing caused by Jupiter's gravity, which generates heat deep below the surface. Geysers occasionally erupt through cracks in the crust, releasing plumes of water vapour into space. Scientists believe that beneath those icy shells could be environments similar to Earth's hydrothermal vents, places where heat, water, and chemistry meet, where life could arise even without sunlight. The same might be true for Enceladus, a small moon of Saturn. When the Cassini spacecraft flew through its icy plumes, it detected organic molecules, the building blocks of life. No one knows what lies beneath its frozen surface, but the idea that tiny oceans under ice could host something living has changed how we think about habitability. It's no longer limited to the warmth of a star. Life might exist anywhere. Energy and chemistry intersect, even in places that seem desolate from above. Then there are the truly alien environments. Lava worlds where surfaces melt and reform daily. Planets covered entirely by clouds of silica vapour, or those that orbit so close to their stars that their atmospheres are being stripped away into space. One such world, K2141b, is thought to have a surface ocean made of molten rock, with supersonic winds carrying vaporized rock from the hot side to the cold, where it condenses and rains down again as stone. It's a planetary version of Earth's water cycle, but instead of rain and rivers, it's a cycle of rock and vapour. What seems unimaginable becomes another pattern of balance, another example of how nature repeats itself in different materials. There's something strangely comforting about knowing that these extremes exist. They give context to our own stability. Earth feels balanced, temperate, calm, because we can now see what lies beyond those limits. The world of fire shows us what happens when energy overwhelms. The world of ice shows us what happens when it retreats. Between them, life finds its narrow window of comfort. Without the extremes, we might never appreciate the rare equilibrium we inhabit. Still, scientists study these planets not just for comparison, but for understanding. Every extreme world teaches us something about physics, chemistry, and the processes that shape planets. The hot Jupiters reveal how migration works, how giant planets can form far from their stars and then drift inward over time. The frozen worlds show how ice and rock interact, how atmospheres evolve or vanish. The more we learn about them, the clearer it becomes that planets are not static. They're dynamic, restless, constantly reshaping themselves, and somewhere in all that diversity, there are probably worlds that began as extremes but found a way toward balance. Maybe a once frozen planet warmed as its star brightened. Maybe a scorched one cooled as its orbit shifted, or as clouds thickened to reflect heat. Planetary climates are not fixed. They change over time, sometimes drastically. Earth itself has swung from ice ages to hothouse periods, from fire to frost, and each time life adjusted. Perhaps elsewhere on distant worlds similar cycles play out, long arcs of change that eventually bring stability. When astronomers model these distant planets, they often talk about equilibrium, the point where energy in equals energy out. That balance determines whether a world burns or freezes. On a hot planet, more energy is absorbed than released, creating runaway heating. On a cold one, the reverse happens, but at the edge of each extreme, there's always a threshold, a line where balance might just be possible. Somewhere, between lava and frost, between brightness and shadow, lies the faint possibility of comfort. And even if life can't survive on the surfaces of these worlds, their existence expands our definition of what's natural. They remind us that the universe doesn't conform to our expectations. It produces beauty from physics alone. Glowing skies, frozen plains, rivers of ice or magma, all born from simple forces playing out across time. In the quiet of the night, thinking about those distant worlds can feel strangely grounding. We live on a planet where temperatures range from freezing to scorching, yet we survive, even thrive, within that range. On a cosmic scale, we inhabit the middle ground between extremes. When you step outside and feel the warmth of sunlight fade into the coolness of evening, you're standing on that narrow edge, the line between fire and ice. It's easy to forget how rare that balance is. And so, as we map these distant, uninhabitable worlds, we're also learning about the limits of habitability itself. How close can a planet be to its star and still retain an atmosphere? How cold can it be and still keep an ocean liquid beneath its surface? These are not just academic questions. They define where life might exist, where we might one day find company, or even where we might go ourselves. The search for other Earths depends on understanding these extremes, because it's in their contrast that we find the pattern. Fire and ice mark the boundaries. Between them lies the small, habitable middle, the space where water flows and chemistry breathes. Without the knowledge of what's too much or too little, we wouldn't know where to look for just right. There's also something philosophical about these worlds. They show us that the universe is both indifferent and creative. It doesn't avoid discomfort. It explores it fully. It creates planets of unbearable heat, of endless cold, of perpetual storms, and still, out of that chaos, it occasionally shapes something balanced, something alive. That balance, fragile as it is, may be the rarest thing in the cosmos, and yet, somehow, we've found ourselves inside it. When the James Webb Space Telescope takes its long, patient observations, it often looks at these extreme planets first. They're bright, their signals strong, their atmospheres easier to study. From their fiery and frozen skies, we're learning the chemistry of other worlds, the nature of alien weather. Someday, that same understanding will help us recognize a truly Earth-like planet when we find one. Every storm we study, every temperature we measure, every atmosphere we decode brings us closer to recognizing the delicate conditions that allow life to exist at all. The worlds of fire and ice may not be homes, but they are teachers. They show us how planets evolve, how atmospheres change, how heat and cold sculpt everything they touch. They reveal the full spectrum of possibility, from inferno to abyss, and remind us that Earth, with all its variety of climates, is part of that same continuum. We are, in a sense, both fire and ice too, carrying within us the heat of creation and the coolness of stability. Everything we know about the universe, almost everything we have ever discovered beyond the reach of our hands, has come to us through light. Not the harsh light of day, but the soft, ancient kind that travels across emptiness for thousands, sometimes millions, of years before touching the glass of a telescope. It's the messenger of the cosmos, the quiet language through which the universe tells us its secrets. Every star, every planet, every nebula speaks in it, each with its own tone, its own rhythm, its own subtle dialect. And we have spent centuries learning to listen. When we look up at the night sky, we're not really seeing stars as they are, but as they were. Their light left long ago, carrying with it the memory of their brightness, their colour, their motion. What we receive is a delayed message, a letter from the past written in photons instead of ink. Some of those letters are still travelling, their words incomplete. Others arrive constantly, each one a tiny piece of the grand conversation between matter and space. To understand how light speaks, you have to think about what it really is. It isn't just brightness, it's energy, oscillating waves that move through a vacuum faster than anything else in existence. Depending on their frequency, those waves can be visible as colour or invisible as heat, radio, X-rays or ultraviolet rays. Every wavelength carries information, encoded in ways we've learned to translate. It's a universal code, a language written in physics, not words. For centuries, astronomers could only see light in its visible form, the narrow band our eyes can perceive. They looked through telescopes, sketched what they saw, and learned to read brightness and motion. But the real transformation came when we learned to break light apart. When a beam of light passes through a prism, it spreads into a rainbow, separating into its constituent colours. Each colour corresponds to a different wavelength, and within those wavelengths lie patterns, dark lines and bright bands that reveal the fingerprints of atoms. Those patterns, known as spectra, are how we learn to read the universe. Every element leaves its own unique set of marks on a spectrum. Hydrogen, helium, oxygen, iron. Each one absorbs and emits light at specific wavelengths, producing distinct signatures. By studying those signatures, Scientists can determine what stars are made of, how hot they are, how fast they move, and even what kinds of planets orbit them. It's like reading a barcode, except the code comes from the oldest forces in nature. When astronomers first used spectroscopy in the 19th century, they made discoveries that seemed almost magical. They found that the sun contained the same elements found on Earth, that stars were not made of some celestial material, but of the same matter that fills our world. It was a revelation, a proof that the universe is continuous, that everything we see above is made from the same ingredients as everything below. That quiet realization erased a boundary. It told us that we belong here, not as exceptions, but as participants in a single shared reality. Light became our primary tool for exploration. Long before we could send spacecraft to other planets, we could study their reflected light and learn about their surfaces and atmospheres. When we observed Mars, we saw traces of carbon dioxide in its thin air. From Venus, we read the signature of sulfuric acid clouds. From Jupiter and Saturn, we learned about hydrogen, helium, ammonia, and methane. Every photon captured was a clue, every wavelength a word in a story we were slowly learning to read. The same techniques are now used to study planets around other stars. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere before reaching us. In that filtered light are faint imprints, tiny differences in colour and intensity that correspond to gases in the atmosphere. By analysing them, scientists can tell whether a planet has water vapour, carbon dioxide, methane, or other compounds that might support life. It's astonishing to think that by studying the tiniest changes in starlight, we can infer the chemistry of a world hundreds of light years away. But reading light is an act of patience. The signals are faint, the noise immense, and the distances beyond comprehension. A single observation might require weeks or months of continuous measurement, and even then the result can be uncertain. Yet every bit of progress adds to the collective understanding. We've now detected atmospheres on dozens of exoplanets, measured their temperatures, and even glimpsed hints of clouds or hazes drifting across their skies. The most remarkable part is that we can do all of this without ever seeing the planets themselves directly. For most, the stars they orbit are tens of thousands of times brighter, drowning their light completely. But their presence still shows up in the star's spectrum, a faint, rhythmic wobble in the wavelengths, caused by the planet's gravitational tug. It's like hearing a duet in which only one singer's voice is audible, yet the music still reveals the other's existence. This is what makes light so powerful. It carries not only the brightness of stars, but the subtle imprints of everything that touches it. Dust clouds scatter it, gases absorb it, planets reflect it. Each interaction leaves a signature, and when we decode those signatures, we reconstruct the invisible. Light lets us see without seeing. It's hard to overstate what that means. Imagine standing on Earth, separated by unimaginable distances from everything else in the galaxy, yet being able to describe what distant planets are made of, how fast they spin, what their weather might be like. That's what spectroscopy allows us to do. We've measured the winds on exoplanets, thousands of kilometers per hour, by detecting the Doppler shifts in their light. We've mapped temperature differences between their day and night sides. We've even inferred the presence of clouds that could rain exotic substances like glass or titanium. All of it comes from light, and all of it happens without leaving our own planet. But beyond the science, there's something almost poetic about how light serves as both the messenger and the message. Every photon that reaches us has travelled across the vast silence of space, carrying within it the story of where it came from. It's as if the universe is constantly writing letters, and our telescopes are simply learning to read them better. In the faintest starlight there's history, billions of years of it. Some of the photons striking your eye tonight left their stars before humanity existed. They crossed interstellar space, slipped through clouds of gas, past drifting comets and distant worlds, before finally finding their way here. That light has survived everything: collisions, absorption, scattering, expansion. It arrives quietly, unassuming, and in it is the memory of a star's birth, its chemistry, its age. When you look at the night sky, you're literally seeing time made visible. That's why astronomers sometimes say that the universe is transparent but not silent. It speaks constantly through light. Every wavelength, from the long lazy hum of radio waves to the sharp flash of gamma rays, carries a different kind of information. Radio waves reveal structure, the shape of galaxies, the remnants of supernovae, the cosmic web that holds everything together. Infrared light pierces dust clouds, showing us newborn stars hidden from optical view. Ultraviolet light traces energetic processes, like the births and deaths of stars. X-rays reveal the violent edges of space, where black holes feed and magnetic fields twist. Together they form a spectrum, a complete vocabulary for describing everything that exists. When you look at the Milky Way stretching across the night, what you see with your eyes is only a sliver of that full conversation. The visible light is the melody, but beneath it hum countless harmonies we can't perceive without instruments. Telescopes tuned to different wavelengths reveal a universe far more complex than the one we see directly. What looks like a soft ribbon of stars in visible light becomes a web of dust in infrared, a network of energy in radio, a storm of high-energy particles in X-rays. Each version is true, each adds a new verse to the same ongoing story, and what's extraordinary is that this story connects everything. Light doesn't discriminate. It moves freely, spreading across billions of years, weaving together galaxies, stars, planets, and observers. It's what allows us to see and to be seen. Even now, Earth is broadcasting its own faint light into space. Radio transmissions, reflections of sunlight, the glow of cities at night. To a distant observer with sensitive enough instruments, our planet would shimmer with a distinctive spectrum marked by oxygen, water vapour, and the soft warmth of life. In that sense, Earth itself speaks the language of light. The thought that light carries our existence outward is strangely comforting. Somewhere, millions of years from now, the photons reflecting off the oceans today might pass through another star system. They'll be faint, almost lost among the countless others, but they'll carry the imprint of our atmosphere, our seasons, our civilization. Perhaps one day, someone, or something, will detect that signal and wonder about the small, bright world that once was. Learning to read light has made us listeners in a vast conversation, and the more we listen, the more we realise how subtle that conversation is. Light doesn't shout, it whispers. It requires patience to understand. The faint dips in a star's brightness, the delicate shifts in its colour, these are the syllables of a language written in time. Decoding them demands not just instruments but attention, the kind of quiet focus that feels almost meditative. Astronomers often spend years analysing a single set of observations, teasing meaning out of noise. It's a process of listening, filtering, interpreting. And while the work is technical, there's also a kind of reverence in it, the awareness that you're reading something ancient, something that has crossed unimaginable distances to reach you. Sometimes, the light reveals things we didn't expect. In 1995, astronomers discovered a distant star whose light dimmed irregularly, as though something enormous were passing in front of it. The dimming didn't match the pattern of a planet. It was too uneven, too complex. Speculation ran wild. Comets, dust clouds, even alien megastructures. The mystery turned out to be natural, of course, a cloud of debris most likely, but the moment captured something essential about our curiosity. We look at light not just to measure but to imagine. Every anomaly, every flicker invites a question, and that question draws us deeper into the unknown. In recent years, our instruments have become sensitive enough to detect the faintest details in starlight, changes of a few parts per million. The James Webb Space Telescope, with its precision and reach, has already begun reading the atmospheres of distant worlds, detecting carbon dioxide, water vapour, and other molecules in planets hundreds of light years away. For the first time, we're not just finding planets. We're starting to sense their climates, their skies, their conditions. Each detection is another line in the universe's unfolding text. And perhaps the most remarkable thing is that all this complexity, all this richness, comes from something so simple. Light, at its core, is just energy moving through space. But in its movement, it carries structure, pattern, and meaning. It's the thread that ties everything together, from the first stars that lit up the darkness to the eyes reading these words. Sometimes it's easy to forget that even our own vision is a kind of translation. The colours we see are the result of light interacting with our senses, a tiny fragment of the spectrum our bodies happen to interpret. Every moment of sight, every sunrise, every glint of reflection is the same process scaled down. Light carrying information, decoded by a receiver. The universe communicates constantly. We are simply tuned to a narrow frequency. When you look up at the stars tonight, you're participating in that communication. You're catching photons that have travelled across time, interpreting their message in your own quiet way. The twinkling you see isn't the stars themselves flickering, but their light bending as it passes through Earth's atmosphere. A reminder that even messages from space must cross layers of imperfection before they reach us. And yet, they reach us still. The language of light is the oldest one we know, and perhaps the most honest. It doesn't exaggerate or withhold. It just moves endlessly, carrying truth through emptiness. Every discovery we've ever made about the cosmos, every star, every planet, every galaxy, has spoken through it. And as we continue to refine our tools, as we learn to listen more carefully, the universe grows a little less silent, a little more familiar. It's strange to realise that the same light we use to understand the stars is the same light that sustains life here. The sunlight that warms the oceans, drives the winds, and nourishes the plants that feed us. In that sense, studying light isn't just astronomy. It's self-reflection. It's understanding the connection between our own warmth and the distant fire of other suns. If there is one substance that ties everything living together, it's water. Every form of life on Earth, no matter how simple or complex, depends on it. It's the medium in which chemistry becomes biology, the quiet stage where molecules find each other and begin to react. When scientists look for signs of life elsewhere, they look for water first, not because it's the only possibility, but because it's the one we understand best. It's the whisper beneath every biological process, the subtle rhythm that runs through everything that breathes, grows, or moves. On our planet, water covers more than 70% of the surface, but it's easy to forget how rare that might be. It flows in rivers, freezes in glaciers, hangs in clouds, and hides in underground aquifers. It moves constantly, evaporating, condensing, falling again as rain or snow, cycling through the air and soil in a pattern so reliable that we take it for granted. But if you were standing on a distant planet, even one roughly the same size as Earth, there's no guarantee you'd find anything like it. For all the billions of planets we've discovered, none yet show oceans we can see, waves breaking, or clouds like ours drifting through blue skies. And yet, we keep searching, because water is the one clue that makes everything else possible. Part of what makes water so extraordinary is its versatility. It's the only common substance that exists naturally in all three states, solid, liquid, and gas, within the narrow temperature range we experience here. That simple property gives rise to weather, to rivers, to oceans, to everything that makes the surface of a planet dynamic. It shapes continents, moderates climate, and carries nutrients that sustain ecosystems. Without it, Earth would be silent and still. On a molecular level, water is deceptively simple. just two hydrogen atoms bonded to one oxygen atom. But the way those atoms are arranged gives it properties that defy expectation. Its molecules are polar, meaning they have a positive side and a negative side. That polarity allows water to dissolve almost anything, making it the universal solvent. It also causes water molecules to cling to each other, forming surface tension strong enough for insects to walk on, for droplets to form and fall. When it freezes, water expands instead of contracting, making ice lighter than liquid water. That quirk means lakes freeze from the top down, leaving liquid water beneath where life can survive through winter. Each of these properties seems perfectly tuned for complexity. They're not magical, they're physical, but together they create an environment that welcomes life. When astronomers search for habitable worlds, they often use the phrase, "follow the water." It's a practical rule, but it's also a philosophical one. Water means energy exchange. It means chemistry and motion. It means the potential for stability and change at the same time. Without it, even if a planet had all the right elements, those elements might never meet in ways that allow life to emerge. The search for water beyond Earth began close to home. The Moon, once thought completely dry, was found to contain traces of frozen water in its shadowed craters. Mars, long imagined as dusty desert, turned out to have ancient river valleys, dried lake beds, and polar caps of ice. Some orbiters have detected seasonal streaks that might be caused by briny liquid water flowing down slopes. Underneath its frozen surface, Mars may still harbour subsurface reservoirs, remnants of a wetter, warmer past when oceans may have spread across its surface. That possibility has reshaped how we see the planet. It's not just a dead world, it's a frozen record of a time when water, and perhaps life, had a chance to begin. Farther out, the search led to the icy moons of the gas giants. Europa, orbiting Jupiter, is covered in a crust of ice that's riddled with cracks and ridges. Beneath that crust lies an ocean of salt water, kept liquid by the gravitational tug of Jupiter and its other moons. The pressure and heat generated by that tidal flexing could create conditions similar to the deep-sea vents on Earth, where life thrives without sunlight, feeding on chemical energy instead of light. Those vents are thought to resemble some of the earliest habitats on our own planet, places where simple organisms might have first formed. If similar conditions exist on Europa, it could mean life doesn't need a warm surface or a shining sun. It only needs water and time. Then there's Enceladus, a smaller moon orbiting Saturn. It too hides an ocean beneath its icy shell. When the Cassini spacecraft flew close in 2005, it detected geysers erupting from cracks near the moon's south pole, plumes of water vapour and ice particles shooting hundreds of kilometres into space. When Cassini passed through those plumes, its instruments found salts, organics, and hydrogen, all ingredients that could support microbial life. It was one of the clearest signs yet that the recipe for life might exist in places we once thought impossible. These discoveries have broadened our view of where habitability might exist. We used to think that life could only thrive on planets like Earth, in temperate zones bathed in sunlight. Now we know that even the coldest, darkest corners of the solar system can hide oceans beneath their ice. The concept of the Goldilocks zone, while still useful, seems too narrow. Water, it turns out, doesn't need perfect conditions. It finds ways to exist even in extremes. On some worlds, like Titan, another moon of Saturn, water exists in a different form altogether. The surface of Titan is far too cold for liquid water, but it has lakes and rivers made of methane and ethane. Yet beneath that frozen landscape, models suggest a subsurface ocean of water mixed with ammonia. It's a strange mirror of Earth, a world where rivers and clouds exist but with entirely different chemistry. If life exists there, it would be unlike anything we've ever seen, perhaps based on methane instead of water, showing us that even the whisper of life might have more than one voice. The question of why water is so essential brings us back to chemistry. On Earth, all biological reactions take place in water because it allows molecules to move freely and interact, It provides a medium that's stable yet flexible, able to store and release heat without dramatic swings in temperature. That stability allows fragile molecules, like DNA and proteins, to form and persist. In a way, water is both cradle and shield. It cushions the birth of life and protects it from extremes. It's not hard to see why ancient cultures revered it. To early humans, water was both life and mystery, unpredictable, powerful, necessary. Rivers carved their paths through landscapes and civilizations. Oceans set the boundaries of the known world. Rain was both blessing and warning. Even now, with satellites mapping every drop on Earth, we still feel that reverence. We still seek its sound to calm us, its rhythm to remind us of continuity. It's no coincidence that recordings of waves and rainfall are used to help people sleep. Water has always been the sound of safety, the background hum of home. When we imagine alien oceans, we often picture something familiar. Blue waves under alien suns, currents, tides, perhaps islands. But the truth is likely more complex. On Europa, the water may be dark and pressurized, more like the abyssal depths of Earth's oceans. On Enceladus, it may be filled with minerals and gases, its chemistry constantly stirred by geothermal energy. On rogue planets, water might exist as high-pressure ice, or deep, hidden seas warmed by internal heat. In each case, the same molecule takes on new forms, adapting to the physics of its surroundings. It's flexible enough to exist almost anywhere, and that flexibility might be what makes it so central to the story of life. Even in interstellar space, the vast regions between stars, water has been found. Radio telescopes detect its signature in the cold clouds of gas where stars are born. It forms on dust grains, freezes, melts and reforms, travelling from one generation of stars to the next. When new solar systems emerge, much of that water ends up locked inside comets and asteroids. Those icy bodies become delivery systems carrying water to young planets. That's how many scientists think Earth got its oceans, through countless impacts from comets and water-rich asteroids billions of years ago. Each collision added to the growing reservoir until liquid water pooled and stayed. In that sense, water is both a product of the cosmos and its messenger, linking the birth of stars to the birth of worlds. The search for water on exoplanets follows the same logic. When a planet passes in front of its star, scientists analyze the starlight that filters through its atmosphere. Water vapor leaves a distinct signature, specific absorption lines in the infrared spectrum. Detecting those lines tells us that water exists in gaseous form, perhaps as part of a cloud system or weather cycle. We've already found it in several exoplanet atmospheres, including those of hot Jupiters and super-Earths. In some cases, those planets are too hot for life, their water existing as steam, but the fact that it's there at all proves that water is common. The building blocks for habitability are not rare, they're scattered across the galaxy, waiting for the right combination of temperature and time. It's easy to think of water as ordinary because it's everywhere here, but in cosmic terms it's a wonder. Hydrogen, the most abundant element, and oxygen, which forms readily in stars, are both common, yet the conditions that allow them to combine and remain liquid are delicate. Planets need enough gravity to hold an atmosphere, enough warmth to prevent freezing, and enough protection to keep their water from being stripped away by radiation. Earth happens to meet all those conditions, but that luck is not guaranteed. Venus likely had water once, but it boiled away under a runaway greenhouse effect. Mars had it too, but lost its atmosphere, and with it, its ability to hold liquid water on the surface. Water, it seems, is as temporary as it is essential. That transience gives it a kind of emotional weight. To know that something so vital can vanish so easily makes its presence more precious. When we look for it elsewhere, we're not just searching for the potential of life. We're searching for continuity, for connection, for some sign that the universe shares the same chemistry that sustains us. Every detection of water, no matter how faint, feels like recognition, a reflection of our own planet echoed in the light of another. In recent years, scientists have begun finding entire worlds that might be water-rich, planets larger than Earth but smaller than Neptune, with thick atmospheres and deep global oceans. These water worlds might have layers of high-pressure ice at their depths, oceans hundreds of kilometres deep, and clouds of vapour above. They're not like Earth, but they're not entirely alien either. If even a few of them fall within their star's habitable zones, they could be teeming with possibilities. The presence of water, though, doesn't automatically mean life. For life to exist, water must stay liquid long enough for chemistry to take root. It must circulate, mix, flow. It must interact with minerals and energy sources. That's why scientists look for signs of both water and geological activity, volcanism, tectonics, or tides that keep the environment dynamic. On Earth, the meeting of water and rock created rich chemical environments where complex molecules could form. Elsewhere, the same principles may hold true. The question isn't whether water exists, but whether it moves, whether it changes, whether it has time to create something new. When we finally do find a planet with evidence of oceans, real oceans, not ice or vapour, it will be a turning point. Seeing a world with surface water would mean seeing the potential for a familiar kind of life, for weather, for climate, for all the quiet processes that make a planet feel alive. It would be the closest thing to recognising a sibling in the vast family of the galaxy. Until then, we keep following the traces, the subtle clues left in starlight. We listen for the whisper of water in the spectrum, the slight bends and dips that say, "I'm here." Every time we find it, we take another step toward understanding how common or rare life might be. And even if we never find another world quite like ours, the search itself teaches us something important, that life, wherever it exists, is likely built on the same principles of connection and change. Water is a reminder that life isn't static. It moves, it cycles, it transforms. It falls from the sky, seeps into the ground, evaporates into clouds, and begins again. The same molecules that once drifted in Earth's early atmosphere now fill our oceans, our blood, our breath. They have moved through every creature that has ever lived. When you drink a glass of water, you are partaking in something ancient. Hydrogen forged in the first stars, oxygen born in later ones, combined and recycled through eons of planetary history. In that sense, every drop of water is a memory of creation, carrying within it the story of both destruction and renewal. If the universe has taught us anything, it's that life has a tendency to hide. On Earth, it doesn't only flourish in the bright, temperate places where sunlight and warmth seem most welcoming. It also thrives in the shadows, in the depths, in the cracks where light never reaches. It hides in the dark corners of the oceans, miles beneath the surface, where the pressure could crush steel and the temperature hovers just above freezing. It survives in caves sealed off from the sky, in deserts where rain might not fall for centuries, in the thin air of mountain peaks where the wind is sharp and cold. Even in the radioactive ruins left behind by humans, life persists. Simple, small, but still there. That resilience has reshaped our understanding of what habitable really means. It has made scientists wonder whether across the galaxy, life might exist not only in obvious places but in hidden ones. The term habitable zone still matters, but it has softened over time. It's no longer just a narrow band around a star where water can stay liquid. It has expanded into a broader idea, one that includes the sheltered, the underground, the unseen. If life can exist in the most unlikely corners of Earth, why not in the protected spaces of other worlds? The more we study the extremes, the more we realise that habitability might be as much about protection as it is about proximity. Life may not always need an open sky. Sometimes it just needs a place to hide. The first of these hidden havens that captured our attention were the icy moons, Europa, Enceladus, Titan, each one with its own kind of secrecy. On their surfaces they appear lifeless, frozen, and still. But beneath their shells of ice lie oceans, vast dark seas that may have existed for billions of years. There, heat from the gravitational pull of their giant host planets keeps the water from freezing solid. In those oceans, minerals from the rocky cores below might mix with water and energy, creating the perfect conditions for chemistry to take root. If life exists there, it would never see sunlight. It wouldn't rely on photosynthesis, but on chemical energy, perhaps from hydrothermal vents like those found at the bottom of Earth's oceans. On our planet, those vents support entire ecosystems, from bacteria to tube worms to crustaceans, all thriving in total darkness. The energy that sustains them comes not from the sun but from the planet itself. The same could be true on those distant moons. The possibility that alien oceans might hide their own ecosystems beneath kilometres of ice is no longer speculation. It's one of the most promising ideas in astrobiology. Europa, in particular, feels like a world of potential. The ice that covers it is cracked and ridged, constantly shifting, suggesting that the surface is active, that the ocean below is not isolated. The gravity of Jupiter stretches and squeezes the moon as it orbits, generating heat through friction in its interior. That same tidal energy likely drives currents in its ocean, cycling nutrients and minerals. If you could dive beneath its crust, you might find an environment surprisingly similar to Earth's deep seas, cold, dark, but alive with chemistry. The thought that life might exist there, shielded from radiation, evolving quietly for eons, is both thrilling and humbling. Enceladus offers another kind of haven. Its plumes, jets of water vapour and ice, erupt through fissures near its south pole, spraying into space. When the Cassini spacecraft flew through them, it found not just water, but organic molecules, salts, and even hydrogen gas. Those findings hinted at hydrothermal activity on the ocean floor, vents where water meets rock, creating gradients of energy that could sustain microbial life. It's remarkable to think that a world so small, barely 500 kilometres across, might harbour an ocean with all the ingredients necessary for life. What makes it even more intriguing is that it's accessible. The plumes themselves release material from the ocean into space, where future missions could sample it directly. Enceladus might be the only place in the solar system where we could search for alien life without landing or drilling, just by flying through the spray of an icy geyser. Then there's Titan, Saturn's largest moon, with its thick orange atmosphere and methane lakes. On the surface, it's unimaginably cold, far below the freezing point of water, but that same surface holds rivers and seas made of liquid hydrocarbons. It's the only other place in the solar system where rain falls and rivers flow, though the rain is methane, and the rivers carve through frozen plains of organic material. Beneath that strange landscape may lie another ocean of water mixed with ammonia, warmer and more suitable for life. Titan is a paradox, familiar yet alien, dynamic yet quiet. It reminds us that habitability isn't always a matter of comfort. It can take many forms, each one shaped by its environment. Beyond the icy moons, other hidden havens may exist closer to home. Mars, though dry and cold on the surface, shows signs of subsurface ice and perhaps even intermittent briny flows. The planet's surface is exposed to radiation, but underground, a few meters down, conditions might be more stable. Ancient river valleys and deltas suggest that Mars once had a thick atmosphere and flowing water. If life began there during that warmer era, it might have retreated underground as the planet cooled and its atmosphere thinned. Microbial colonies could persist in pockets of moisture, waiting quietly in the dark. Several upcoming missions, including robotic drills and sample return projects, are designed to look for exactly that. Traces of life beneath the surface, hidden from view but preserved in stone. Even asteroids and dwarf planets could host small temporary havens. Ceres, the largest object in the asteroid belt, has bright patches of salt deposits that hint at briny liquid water beneath its crust. Some scientists think that subsurface oceans might exist there too, kept liquid by internal heat or chemical reactions. The universe, it seems, has many ways of storing its water, many ways of tucking away the raw materials for life. It hides them beneath ice, under rock, within the folds of gravity. If life does prefer to hide, it's not hard to understand why. The surface of most worlds is hostile, bombarded by radiation, frozen or scorched, exposed to vacuum or violent storms. Beneath the surface, conditions can be steadier. There, water can remain liquid, temperatures can stay constant, and chemistry can proceed undisturbed. Even on Earth, some of the oldest microbial life exists underground, kilometers deep, feeding on chemical reactions between rock and water. Those subterranean organisms live in total darkness, independent of sunlight, in ecosystems that may have been stable for billions of years. It's possible that the same kind of life could exist beneath the crusts of other planets and moons, not as a rarity, but as the most common form of life in the universe. This idea changes how we think about exploration. Instead of looking only at the surfaces of planets, we're now learning to look deeper. Missions are being designed to drill through ice, to listen for the vibrations of subsurface oceans, to send probes that can melt their way downward through frozen crusts. Future explorers might not walk on the surfaces of alien worlds, but swim beneath them, guided by instruments that can read chemistry and temperature in the dark. Hidden havens could also exist on planets that seem, from a distance, completely uninhabitable. A planet orbiting close to its star might have a scorched surface, but beneath layers of rock, cooler regions could persist. There, groundwater could exist, shielded from radiation. On the other end of the scale, a frozen planet drifting far from its sun might have a subsurface ocean heated by internal decay or tidal forces from a nearby moon. We're beginning to realize that surface conditions might be the least reliable indicator of habitability. A dead-looking planet could be teeming with hidden life, while a beautiful blue world could be sterile beneath its clouds. The possibility of underground or underwater life also raises questions about how such life might communicate or evolve. Without light, vision would be useless. Organisms might rely on vibration, chemistry, or even electrical signals to sense their surroundings. Evolution could take entirely different paths, shapes, metabolisms, and behaviours that make sense only in the context of darkness. On Earth, deep-sea creatures glow, pulse, and drift in ways that seem alien, yet every one of them follows the same basic rule: adapt to what is available. In the oceans of Europa or Enceladus, life, if it exists, might look more like bacteria or simple multicellular organisms. It might be slow, cold, and patient, not driven by light, but by chemistry, by time. In a way, these hidden habitats reflect something about the universe itself. It doesn't advertise its wonders. It conceals them beneath layers, revealing them only to those who look closely, who are willing to search in places that appear lifeless at first glance. Each discovery, an ocean beneath ice, organic molecules in a plume, traces of methane in a thin atmosphere, is a reminder that appearances can deceive. A silent world can hold a secret ocean. A frozen crust can cover warmth. A barren landscape can shelter life. This quiet persistence is part of what makes the search so moving. It's not just about finding evidence of life. It's about understanding the conditions that allow it to endure. If we do find life beyond Earth, it probably won't announce itself with signals or cities. It will be found in a droplet of water, a chemical imbalance, a subtle pattern in the light. It will be something small, steady, and ancient, proof not of conquest but of continuity. These hidden havens also invite us to think differently about what alive means. If life exists underground, without sunlight or oxygen, feeding on minerals or chemical gradients, it challenges our earth-bound definitions. It suggests that life is not a rare outcome, but a natural extension of physics, a pattern that emerges wherever energy and stability coexist. It could mean that life is common, but mostly invisible, thriving out of sight across billions of worlds. As we keep searching, our instruments grow more sensitive, our questions more refined. The next generation of space probes may be able to detect biosignatures, chemical traces of life, directly from orbit. Others might land on icy moons, drilling into the crust or sampling the plumes. One day, perhaps not far from now, we may hold in our hands the evidence of life from another world, hidden for eons beneath ice or rock, waiting for us to find it. And when that happens, it will not only answer a scientific question, but raise an existential one. If life can thrive in darkness, if it can endure in isolation, then perhaps it's not the exception but the rule. Perhaps the galaxy is full of hidden havens, not empty, but occupied quietly, patiently, in ways we've only just begun to imagine. Even here on Earth, most of our biosphere is unseen. The vast majority of life exists beneath the surface or beneath the sea, in forms too small for the eye to detect. We live surrounded by hidden ecosystems, and yet we rarely notice them. It's a fitting metaphor for the universe as a whole, full of unseen life, full of quiet persistence. We don't have to look far to understand that the invisible can be the most abundant. So when astronomers peer into the cold distance and study the faint signatures of ice and vapour, they're not just mapping geology. They're looking for the same pattern we see at home, the pattern of shelter, of endurance, of quiet survival. The universe may seem vast and indifferent, but within its cold depths, it appears to make room for life in the most unexpected places. And as our gaze turns from those buried oceans and underground worlds to the bigger picture, we begin to ask a different kind of question, not just where life might be hiding, but how often it might appear at all. If the galaxy is full of such havens, then how many of them might actually be alive? How many planets, moons, or worlds are not just habitable, but inhabited? When we talk about life beyond Earth, the question almost always turns into a number. Not because we expect an exact answer, but because numbers help us grasp what feels otherwise impossible to imagine. How many worlds could there be like ours? How many stars have planets with oceans or air? How many civilizations might be out there looking back at us, wondering the same thing? Somewhere between the certainty of physics and the uncertainty of hope lies a quiet effort to count the uncountable. It's a kind of gentle arithmetic of possibility, what scientists sometimes call the mathematics of maybe. The most famous expression of that arithmetic is an equation written on a blackboard in 1961 by an astronomer named Frank Drake. He was preparing for a meeting about the search for extraterrestrial intelligence and wanted a way to organize the factors that would determine how many communicative civilizations might exist in our galaxy. What he wrote wasn't meant as a solution, but as a framework, a way to think through the steps that connect stars to life and life to awareness. The equation became known simply as the Drake equation, and though its form is simple, its implications reach across everything we've discussed so far. It goes like this: n r spore x fp x ni x fl x fi x fcxl. Each term represents a stage in the process that might lead from the formation of stars to the existence of intelligent life capable of communication. N is the number of such civilizations that might currently exist in the Milky Way. R is the average rate of star formation in our galaxy. How many new stars are born each year? Fp is the fraction of those stars that have planets. Ne is the average number of planets per system that could potentially support life. Fl is the fraction of those planets where life actually appears. Phi is the fraction where life evolves intelligence. Fc is the fraction of intelligent life that develops technology capable of communication. And L is the average lifetime of such a civilization. At first glance, it looks like simple multiplication, but every variable represents a mystery. We know some of them now better than Drake did. When he wrote his equation, no one had detected a single planet outside our solar system. The term FP, the fraction of stars with planets, was pure guesswork. Today, we know the answer. Almost all stars have planets. Planet formation is a natural part of star formation. It's not the exception, but the rule. That one realization shifted the entire balance of the equation. Suddenly, the number of possible worlds increased from a few rare systems to billions upon billions. The next term, Ni, asks how many of those planets might be capable of supporting life. Here, supporting life usually means existing within a habitable zone, with the right conditions for liquid water. Thanks to missions like Kepler and TESS, we now know that a significant fraction of stars have Earth-sized planets in that temperate zone. Even if only 1 in 5 stars does, that still means tens of billions of potentially habitable planets in our galaxy alone. And that's before counting moons, which might also host oceans beneath their surfaces. After that, the equation moves into deeper uncertainty. The term FL, the fraction of habitable worlds where life actually arises, remains unknown. On Earth, life appeared quickly, almost as soon as conditions allowed. Within a few 100 million years of the planet cooling enough for water to exist, there were microorganisms thriving in the oceans. That speed suggests that life might not be rare when the conditions are right. Chemistry seems eager to organize itself into complexity. But we only have one example, and one example can't define a rule. We don't know whether life begins easily everywhere, or if Earth represents an extraordinary stroke of luck. Then comes Phi, the fraction of life-bearing worlds where intelligence evolves. On Earth, life existed for billions of years before intelligence, as we define it, emerged. Single-celled organisms ruled for most of the planet's history. Complex multicellular life appeared late, and intelligent technological life only in the final fraction of that timeline. Intelligence might be rare, not because it's difficult in principle, but because it's not necessary for survival. Evolution favours adaptability, not self-awareness. Many species thrive without ever questioning the stars. That means Phi could be small, even if life itself is common. The next term, FC, asks how many intelligent species develop technology capable of communication, radios, telescopes, or signals strong enough to cross the void. That too is uncertain. Humans have had such technology for only a little more than a century, a blink compared to our species' age, and an invisible instant compared to cosmic time. Civilizations might rise and fall, invent and forget, or choose not to broadcast at all. Some may exist in silence, inward-looking, their communication methods too different for us to detect. Others might never reach that stage before collapsing or changing into something unrecognizable. Finally, there's L, the average lifetime of a communicative civilization, perhaps the most crucial and most difficult factor of all. Even if intelligent life arises often, if civilizations last only a short time before disappearing, then the galaxy could be full of ruins and echoes, not companions. But if some survive for millions of years, then the odds of overlap, of two civilizations existing at the same time, increase dramatically. L might be the key to whether we ever hear from anyone else. The beauty of the Drake equation isn't in its precision, it has none, but in how it helps us organize ignorance. It turns a philosophical question into a series of scientific ones, each of which can be studied. We can measure star formation rates, we can detect planets, we can estimate how many are in habitable zones. Even if we can't yet measure the later terms directly, we can narrow them down as our knowledge grows. Each discovery fills in another blank, slowly transforming speculation into data. And yet, even as the numbers become clearer, the mystery remains. The equation, for all its order, still leaves room for wonder. It invites us to imagine not just whether life exists, but what form it might take, how it might think, and how long it might endure. It forces us to confront the possibility that the universe could be both teeming with life and profoundly silent at the same time. When scientists plug in values for each term, the results vary wildly. Depending on the assumptions, n can be anything from 1, meaning we are alone, to many millions. Both outcomes fit the evidence we have. It's a reminder that data alone doesn't always resolve uncertainty. Sometimes, the unknown remains unknown not because we lack tools, but because the universe itself keeps its answers diffuse, stretched across too much time and space for a single viewpoint to contain. But the effort to refine the equation continues. The Kepler and TESS missions have given us reliable numbers for the first few factors, studies of extremophiles, organisms that thrive in extreme conditions, suggest that life could exist in environments far more diverse than we once imagined, expanding the plausible range of FL. Advances in astrobiology are helping us model how life might begin chemically. The search for biosignatures, atmospheric gases like oxygen or methane that indicate biological activity, may soon let us estimate Epsilon-5 more directly. We're getting closer to turning some of those maybes into measurements. Still, some parts of the equation might never yield exact answers. The lifetime of civilizations, for instance, depends on choices as much as on physics. It involves politics, ethics, sustainability, and chance. It's a reflection of behaviour, not just biology. In that sense, the Drake equation is as much a mirror as a calculation. It doesn't only describe the galaxy, it describes us, what we value, how long we might last, whether we will choose to preserve or destroy what we've built. Drake himself never claimed the equation could give a precise answer. He used it as a tool for conversation, a way to frame the search for extraterrestrial intelligence in scientific terms rather than speculation. Decades later, it still serves that purpose. Every time we discover a new planet, detect an atmosphere, or measure a star's brightness, we're refining one of those variables, inching closer to understanding our place in the equation. When you look at the sky with this in mind, it changes how the stars appear. Each one becomes not just a point of light, but a potential data point in a grand probability, a small term in the mathematics of maybe. Some of those stars are newborn, still surrounded by disks of gas and dust where planets are forming. Others are ancient, their worlds long settled or long gone. Each could be part of the count, part of the quiet arithmetic that tells us how common life might be. If even a tiny fraction of those billions of stars host life, the numbers grow staggering. Suppose 1 in 10,000 planets develops intelligent life. In a galaxy with hundreds of billions of planets, that would still mean millions of civilizations over cosmic history. Most may have come and gone, but even a handful existing now would make the universe far less lonely. The problem, of course, is that distance and time make communication almost impossible. Light takes years to travel between stars, and civilizations may rise and fall before their signals reach each other. The galaxy could be full of voices, but separated by eras, each calling out into a silence that no longer answers. That possibility leads to another question, the one that often follows the Drake equation. If the numbers suggest life should be common, then why haven't we found any evidence of it? This puzzle, known as the Fermi paradox, asks why. In a galaxy so large and old, we haven't detected signs of other civilizations. Perhaps the equation's later terms are smaller than we hope. Intelligence rare, communication short-lived. Or perhaps we're simply listening in the wrong way, or not long enough. The mathematics of maybe doesn't promise comfort. It only promises honesty. A way to measure what we can, and to recognise what we can't. There's something strangely soothing about that uncertainty. It leaves room for imagination without dismissing reason. It tells us that the universe could be full of life and still appear silent from where we stand. It reminds us that silence doesn't mean emptiness. It may simply mean distance or timing, or the quiet modesty of civilizations that prefer to observe rather than announce themselves. Every new piece of data we collect, every signal we analyse adds another layer to the equation. The search for exoplanets has filled in the first few terms with confidence. The next step, detecting life itself, may not be far away. instruments like the James Webb Space Telescope and future observatories will soon be able to analyse the atmospheres of Earth-sized planets for signs of oxygen or methane. If even one such planet shows convincing evidence of biology, the value of FL will leap from speculation to certainty. That single discovery would ripple through the entire equation, multiplying its final answer by unimaginable amounts. And yet, even if we never find proof, the act of searching carries meaning. It reminds us that we're part of a larger pattern, one node in a galaxy full of possibilities. The Drake equation is not a solution waiting to be solved, but a conversation we continue to have with ourselves, balancing data and hope, reason and wonder. Its variables are not just numbers, they are stories about creation, endurance and connection. To think mathematically about maybe is to admit that we live in the middle of uncertainty, that knowledge is always partial, that existence itself may be more common than we can yet prove. It's an act of humility disguised as arithmetic. When you imagine the galaxy through this lens, the darkness between stars starts to feel less empty. Each point of light becomes part of a vast equation still unfolding, an ongoing calculation written across billions of years. The universe, in this view, isn't random. It's statistical. Every star, every planet, every molecule contributes to the sum, even if the total remains unknown. Perhaps in some distant future the variables will narrow enough for us to see the outline of an answer, a number that tells us how often life arises, how often it learns to think, how often it reaches out. Until then, the equation remains open, not as an unfinished problem, but as a reflection of our own curiosity. The mathematics of maybe is the mathematics of hope, structured, reasoned, but still yearning. And as we let that thought settle, as the numbers drift softly into abstraction, the silence of the galaxy begins to take on a different tone. Because if the probabilities are so high and the evidence so elusive, we have to ask why. Why does a galaxy so full of potential seem so quiet? Why does the light bring us information about worlds but no voices from them? The night sky looks peaceful. It gives the illusion of stillness, as though the stars have been there forever and will stay that way forever. But behind that stillness lies an unsettling question that scientists and philosophers have struggled to face. If the galaxy is full of stars and planets, if life arises easily, if intelligence eventually follows, then why is it so quiet? Why haven't we heard from anyone else? The mathematics of maybe suggest that we should not be alone. And yet every search, every listening effort, every faint whisper of radio noise has so far returned the same answer. Silence. That silence feels heavier the more we learn about how common planets are, how stable stars can be, how chemistry seems eager to create complexity. If everything points toward abundance, why does the universe appear so empty of conversation? This question is what physicists and astrobiologists call the Fermi paradox, named after the physicist Enrico Fermi, who famously asked during an informal discussion, "Where is everybody?" It's not a paradox in the strict mathematical sense, but a tension between expectation and observation. Statistically, there should be countless civilizations. Observationally, there are none we can confirm. That gap, the difference between what should exist and what we actually see, has led to one of the most haunting ideas in science, the Great Filter. The Great Filter is not a specific event or object. It's an idea, a hypothesis meant to explain why, in a galaxy that should be full of life, we have found no evidence of it. It suggests that somewhere along the path from lifeless matter to intelligent civilization, there is a barrier, a kind of cosmic checkpoint that most species cannot pass. It could occur early, preventing life from starting in the first place. It could occur later, stopping intelligent life from surviving long enough to communicate. It might be one obstacle or a series of them, but whatever form it takes, the result is the same: silence. To understand why scientists take this idea seriously, it helps to think of the chain of events required to reach a point like ours. First, a star must form in a stable region of the galaxy, far from the violent radiation near the core. Around that star, a planet must form in the right zone for liquid water. That planet must be large enough to hold an atmosphere, but not so large that it becomes a gas giant. It must have the right mix of elements: carbon, nitrogen, phosphorus, and others. It must remain stable for billions of years, avoiding catastrophic impacts or radiation bursts. On that planet, chemistry must somehow give rise to life. That life must endure, diversify, and eventually evolve intelligence capable of building tools, language, and technology. Then, that intelligent species must survive long enough and remain interested enough to send signals or travel between stars. Each of those steps is possible, but each depends on many fragile conditions. Somewhere along that chain, something usually fails. The question is, where? If the great filter lies in the past, before the emergence of life, then we may already have passed it. That would mean the hardest step, the most improbable transition, was the origin of life itself. Maybe chemistry doesn't easily cross the line into biology. Maybe Earth was a rare stroke of fortune, a place where conditions aligned in a way that almost never happens elsewhere. In that case, the silence of the galaxy isn't threatening, it's reassuring. We would be rare survivors in a universe mostly empty because life itself is so unlikely. But if the great filter lies ahead, if the barrier comes after intelligence, then the silence is ominous. It would suggest that civilizations tend to destroy themselves before they become capable of long-term communication or interstellar travel. They might collapse through war, environmental collapse, technological accidents, or the slow decay of interest and capacity. Intelligence may be self-limiting, creative enough to build but not wise enough to endure. That interpretation casts our own future in a different light. It implies that longevity, not intelligence, might be the rarest trait in the universe. There are other possibilities, of course. Perhaps civilizations arise often, but communication is impossible across such vast distances. The speed of light imposes a hard limit. Signals take years, centuries, or millennia to reach other stars. A civilization might broadcast for 1,000 years, but in cosmic terms that's a heartbeat. If no one happens to be listening at the right time, the signal fades into the background. It's entirely possible that the galaxy is full of civilizations separated not just by distance, but by time, too far apart in history to ever overlap. Another idea is that life may be common but quiet by choice. Civilizations might learn that broadcasting their presence is dangerous or simply pointless. They might choose silence as safety, or focus inward rather than outward. Some scientists call this the zoo hypothesis, the notion that advanced civilizations deliberately avoid contact with less developed ones, much as humans avoid interfering with wildlife reserves. It's speculation, but it offers an explanation for the quiet. Maybe we're being watched, but not disturbed. Still, the Great Filter remains the most sobering interpretation. It doesn't assume malice or mystery, only probability. Every species faces challenges: environmental, technological, social. Most of those challenges are self-created, byproducts of intelligence itself. The same creativity that allows a civilization to harness energy can also lead it to destroy the balance that sustains it. The same curiosity that builds weapons can also point them inward. In that sense, the Great Filter may not be an external wall at all, but an internal one, a test of maturity that most fail. When we look at our own world, it's not hard to see how that could happen. Humanity has reached a stage where our technology gives us immense power, but also immense risk. We can alter climates, extinguish species, and change ecosystems faster than nature can adapt. We can create energy that could destroy entire cities. We rely on fragile systems for survival, systems we barely understand in full. Whether by accident or choice, civilizations like ours could easily end long before mastering the skills required to survive for cosmic timescales. But it's also possible that the Great Filter isn't a single catastrophe. It could be a series of smaller ones, slow processes that erode stability, economic collapse, ecological exhaustion, cultural decay, loss of curiosity. A civilization might not fall in fire, it might simply fade, distracted or diminished, its priorities shifting until exploration ceases. In that way, silence could be the natural end state of most intelligent life, not destruction, but disinterest. There's an unsettling symmetry to that idea. The more capable a civilization becomes, the greater the temptation to turn inward, to simulate rather than explore, to replace physical discovery with digital experience. The energy and focus required for interstellar communication might become trivial compared to the allure of self-contained worlds. The Great Filter, then, could be apathy, the quiet narrowing of ambition over time. For scientists, the challenge is that we have no way to test these ideas directly. We can listen for signals, scan for anomalies, search for artifacts, but absence of evidence isn't evidence of absence. A galaxy can appear silent even if it's full of voices we simply can't interpret. The Great Filter remains hypothetical, a model to explain what we can't yet see, but it influences how we think about our future. If the silence is universal, then understanding why becomes essential for survival. Some thinkers have suggested that the Great Filter might even be behind us, not the rise of life, but the leap from single-celled to multicellular organisms. On Earth, that transition took billions of years, suggesting it's rare and difficult. If that's true, then most life in the universe might remain microbial, abundant but simple, widespread but quiet. That would make us unusual, not for existing, but for evolving complexity. In that scenario, the silence isn't a warning, but a confirmation that advanced life is rare. Yet even that interpretation carries weight. If complex life is rare, then our responsibility increases. It means we represent something precious, something fragile, something not easily repeated. It means the silence isn't emptiness, but opportunity. The chance to last where others have not, to pass the filter rather than be stopped by it. When we look up at the Milky Way, we're seeing billions of possibilities, most of which have likely failed to reach the point we occupy now. Somewhere among those stars might be ruins, planets where life once flourished but didn't endure. Not the ruins of cities necessarily, but chemical remnants, fossils or atmospheres that tell stories of what might have been. The universe is ancient, and time erases even the grandest accomplishments. Civilizations could have come and gone long before Earth even formed. Their light would still reach us, but their presence would not. In that sense, the Great Filter might not be a single event, but time itself. The galaxy is 13 billion years old. Our species has existed for only a few 100,000. Even if countless civilizations have risen, their windows of existence might rarely overlap. Imagine lights flickering on and off across the galaxy, each civilization glowing for a short while before fading. From any given point the sky would seem dark, even if countless others had once shone. Some scientists find this explanation comforting. It means the silence isn't a warning, it's a limitation of perspective. We are listening during our own brief moment, unaware of the many that came before and the many that may come after. The universe could be full of life, but we are simply too early or too late to hear it. Still, the idea of the Great Filter has a way of lingering. It forces us to consider not only the universe's possibilities, but our own fragility. It asks whether intelligence naturally carries the seeds of its own extinction, and if so, what we can do to avoid it. It turns astronomy into self-reflection. Every time we point a telescope at the stars and find no signal, we are also looking inward, measuring our own path against the silence. That silence itself is peculiar. The more we study the galaxy, the more we realize it's not just empty space. It's full of radio noise, background radiation, cosmic signals from pulsars and quasars. But amid all that, there's no trace of artificial structure, no clear sign of transmission, No engineered beacons. The search for extraterrestrial intelligence, or SETI, continues with ever-improving sensitivity, scanning billions of frequencies. We found nothing yet, though that nothing is filled with meaning. It tells us that if there are civilizations, they either don't use the kinds of communication we expect, or they're far rarer than probability suggests. One of the most thought-provoking interpretations of the silence is that civilizations might be common, but communication rare because technology changes too quickly. A species might spend only a few centuries using detectable radio waves before shifting to more efficient or internalized methods of communication. To another civilization, that window would appear as a brief flash, a signal that flares and vanishes. If everyone speaks briefly and then goes quiet, it would explain why the galaxy sounds empty. Another possibility is that intelligence tends toward isolation by necessity. Space is vast, resources finite, and survival difficult. Civilizations might choose to focus inward, conserving energy rather than reaching outward. From their perspective, the galaxy might seem too large to cross, too indifferent to engage. The Great Filter might not destroy civilizations, but simply make them retreat. And yet, even in that retreat, there's a quiet kind of harmony. Perhaps the silence we hear isn't loneliness, but balance. A natural state for a universe that values endurance over noise. Communication may not be the ultimate measure of success. Survival might be. A species that endures quietly for millions of years, in equilibrium with its world, could pass the Great Filter without ever broadcasting a single signal. In the end, we don't know which interpretation is true. The Great Filter could be behind us, ahead of us, or scattered across every stage of development. It could be rare or inevitable or entirely illusory, a projection of our own fears. But whatever it is, the silence of the sky remains. It humbles us. It reminds us that intelligence does not guarantee permanence, that progress does not ensure safety, that awareness comes with responsibility. As we continue to listen, the question becomes less about whether anyone else is out there, and more about what kind of future we will choose for ourselves. Will we add to the silence, or outlast it? Will we learn to balance ambition with sustainability, curiosity with care? The Great Filter, in its most optimistic interpretation, is not a doom, but a challenge, an invitation to prove that intelligence can persist. When you think about everything that could have gone differently, everything that had to align for Earth to become what it is, the word that comes to mind isn't luck, though it often feels like that. It's balance. A delicate, persistent balance that has held, somehow, for billions of years. Our planet sits in a narrow orbit, tilted just enough to create seasons, but not so much that the climate collapses into extremes. It has an atmosphere thick enough to protect life, but thin enough to let sunlight through. Its magnetic field shields it from radiation. Its moon steadies its spin. Its oceans regulate its temperature. Every detail, from the size of the planet to the chemical mix of its air, participates in a harmony that allows us to exist. That balance could have broken at any point, but it didn't. It held, and life took hold with it. From space, Earth doesn't look like much. A sphere of blue and white, small against the vastness that surrounds it. But that view hides how complex and improbable it truly is. Every cloud you see, every patch of green, every gust of wind or flash of lightning is part of a system that sustains life. Our atmosphere didn't appear all at once. It was built molecule by molecule over eons, shaped by volcanoes, by photosynthetic organisms, by the slow exchange between air and ocean. The air we breathe today is the product of countless transformations, each one dependent on the ones before it. The oxygen that fills our lungs was once a poison to early life. The nitrogen that cushions it was released from rocks by ancient heat. Even the carbon dioxide we debate so often now was once the foundation for stability. In the beginning, Earth wasn't a hospitable place. It was violent, molten, constantly bombarded by debris left over from the formation of the solar system. Oceans didn't yet exist. The sky was thick with gases that would have suffocated anything alive today. But as the planet cooled, water vapour condensed into rain, and for millions of years it rained without stopping. Those rains filled the lowlands, forming oceans that became the cradle of biology. Within those waters, chemistry began to experiment. Simple molecules combined, broke apart, and recombined again until, eventually, something remarkable happened. Replication. The first spark of life didn't need intelligence or intention. It only needed time and the right conditions. Once it began, life didn't stop. It spread through the oceans, diversifying, adapting, learning the rhythms of survival. Microbes evolved ways to use sunlight, releasing oxygen as waste. Over time, that waste transformed the atmosphere, creating the conditions for new forms of life to emerge. Land, once barren, grew green. The air thickened with new gases, and ecosystems began to shape the planet itself. Life didn't just adapt to Earth, it changed it. Every breath you take, every plant that grows, every ocean current that moves, carries the fingerprints of that ancient relationship between biology and environment. When scientists talk about Earth's habitability, they often mention feedback loops, processes that keep the planet's systems in check. One of the most important is the carbon cycle. Carbon dioxide in the atmosphere traps heat, keeping the planet warm enough for liquid water. When levels rise too high, rain and chemical reactions pull that carbon into the oceans, where it's locked in rocks or taken up by organisms. When levels drop too low, volcanic activity releases carbon back into the air. The balance isn't perfect, but it's stable enough to keep the climate within limits that life can tolerate. That self-regulating system, driven by geology and biology together, is one of Earth's quiet miracles. The presence of a large moon may be another. Our moon is unusually big compared to the planet it orbits. It formed, scientists believe, from a massive collision early in Earth's history, a smaller world striking ours, throwing debris into space that eventually coalesced into a satellite. That impact reshaped everything. It gave Earth its axial tilt and its seasons. The moon's gravity stabilizes that tilt, preventing wild swings that could have caused extreme climate changes. It also stirs the oceans, driving tides that help circulate nutrients and shape coastlines. Without that constant lunar pull, life might have evolved very differently or not at all. Earth's magnetic field provides yet another layer of protection. Generated by the movement of molten metal in the planet's core, it extends far into space, deflecting charged particles from the solar wind. Without it, those particles would strip away the atmosphere, as they did on Mars. The magnetic field isn't something we can see, but its presence makes all the difference. Every aurora that shimmers near the poles is a visible trace of that invisible shield doing its work, catching radiation and turning it into light. Even the arrangement of the solar system contributes to Earth's safety. Jupiter, with its immense gravity, acts as a cosmic guardian, deflecting comets and asteroids that might otherwise strike us. The Sun, steady and long-lived, provides just the right amount of energy, not so much that our oceans boil, not so little that they freeze. The distances between planets, their orbits, their gravitational interactions, all maintain a dynamic equilibrium that has remained remarkably consistent for billions of years. The more we learn about other solar systems, the more we realize how unusual that stability might be. But Earth's balance isn't static. It's been tested many times. The fossil record is filled with evidence of extinction events, mass die-offs caused by volcanic eruptions, asteroid impacts, shifts in climate. Each time, life nearly ended, and each time it recovered, adapting to the new world that followed. The most famous of these events, the asteroid impact that ended the age of dinosaurs, could have erased everything we now know. Instead, it cleared the way for mammals to flourish, for evolution to take a different path, one that eventually led to us. In that sense, even catastrophe plays a role in Earth's story. The planet's resilience lies in its ability to change without breaking. The continents drift, the seas rise and fall, the climate warms and cools, yet life continues to adjust. Coral reefs rebuild after bleaching. Forests regrow after fires. Ecosystems shift and recover. That adaptability is both a strength and a warning. It shows us that the planet can survive dramatic transformations, but it doesn't guarantee that our particular version of life will survive with it. The Earth will endure. Whether we do is another question. When you consider how many things had to go right for life to reach this point, it becomes clear how fragile that balance really is. A slight change in the sun's brightness, a shift in orbit, an increase in greenhouse gases. Any of these could alter the climate enough to upset the equilibrium. We've already begun to see those effects through our own actions. Rising temperatures, melting ice, changing weather patterns. They remind us that stability is not a given. The systems that sustain us are intricate and interconnected. Disturbing one part affects the whole. Still, the fact that Earth has remained habitable for so long is astonishing. The sun has grown brighter over time, yet the planet's climate has stayed within a range suitable for liquid water. That suggests a built-in resilience, a balance between warming and cooling mechanisms that adjust as conditions change. This self-regulation might be unique to Earth, or it might be a general feature of planets with active geology and life. Either way, it's a reminder that habitability isn't a static trait. It's a dynamic state, maintained through countless interactions. Some scientists have suggested that Earth functions almost like a single, living system, not in the sense of consciousness, but in its interconnectedness. The air, water, rocks, and life all influence one another. This concept, sometimes called the Gaia hypothesis, isn't mystical. It's observational. The biosphere affects the atmosphere, which affects the oceans, which affect the land, and the cycle continues. It's a closed loop of feedback and adjustment. When one element shifts, the others respond. The system seeks equilibrium, not because it wants to, but because the laws of physics and chemistry make it so. That self-balancing nature has allowed Earth to recover from events that would have sterilized lesser worlds. It's what lets forests regrow after volcanic eruptions, what allows the oceans to buffer changes in temperature, what lets the climate oscillate without collapsing. Yet even that resilience has limits. The balance that protects life can also be pushed beyond repair. The same feedback loops that stabilize can amplify change if forced too far. Carbon dioxide, for example, warms the planet, but warming releases more carbon from permafrost and oceans, accelerating the cycle. The same chemistry that sustains stability can also tip it into chaos. In that light, Earth's continued livability looks less like inevitability and more like a fragile truce, a temporary agreement between forces that could easily overpower each other. For now, the balance holds. The oceans absorb heat, the forests store carbon, the winds distribute energy, the ice reflects sunlight. Together they keep the system in check. But nothing guarantees that it will always stay that way. The miracle of Earth isn't that it exists, it's that it still works. And yet, despite that fragility, there's strength in how adaptable life has proven to be. Even in the harshest places on the planet, deep beneath the crust, in acidic lakes, in boiling vents, life finds a way to persist. That resilience hints at a universality that goes beyond Earth itself. If life can survive here through all these changes, perhaps it can survive elsewhere too. Perhaps the same combination of chemistry and adaptability repeats across the galaxy. But Earth remains our only example, and that makes it precious. It's the one place where we know life has not only appeared but flourished, diversified, and endured. When astronauts look back from orbit and describe the sight of Earth, the thin blue line of atmosphere, the swirling clouds, the deep oceans, they often speak of how small and vulnerable it seems. From a distance, national borders vanish, cities disappear, and what remains is a living sphere suspended in darkness. It's humbling, but also grounding. It reminds us that everything we know, everything we are, depends on a balance we can barely comprehend. The search for habitable worlds in other systems is, in a sense, a search for mirrors, planets that might reflect some part of what makes Earth special. Each discovery of an Earth-sized planet in a habitable zone raises the question of how many such fragile miracles might exist. Are we a singular occurrence, or part of a vast population of living worlds? The more we look, the more it seems possible that the conditions for life aren't unique. But even if other worlds exist, none will be exactly like this one. Every planet has its own version of balance, its own way of solving the equation of survival. To understand Earth's fragility is not to despair, but to appreciate. It reminds us that our place in the universe isn't guaranteed, that our stability depends on respect for the systems that sustain us. It encourages humility, a recognition that we are participants, not masters, in the planet's ongoing equilibrium. We are products of its chemistry, beneficiaries of its resilience, and stewards of its future. In all the vastness of space, amid all the probabilities and equations, Earth is the only confirmed home for life. It's a small world, fragile yet tenacious, vulnerable yet enduring. Every breath, every drop of rain, every shift in wind is part of the same improbable story. A planet that has balanced chaos and order long enough for consciousness to arise and wonder about its own existence. And as we hold that thought, tracing the outlines of what keeps us alive, the perspective begins to shift again. Because if Earth is a miracle of balance, then the same forces that shaped it, gravity, light, time, and chance, are shaping countless other worlds. The same chemistry that built our oceans and air is at work throughout the galaxy. Somewhere, perhaps far away, those same laws may have combined in different ways, creating other forms of stability, other versions of life. When you begin to think of the universe not as a collection of separate objects, but as a single, continuous process, the image that forms is one of rhythm. Every planet, every star, every molecule participates in it. There's motion, variation, repetition, and feedback, not in the musical sense, but in the way systems respond to each other. Stars form, burn, and fade. Planets orbit, shift, and realign. Light travels, reflects, and disperses. Life, where it appears, becomes another layer in that sequence, another thread in the pattern. It's not a symphony in the human sense of melody or harmony, but it has structure, cycles and interactions that make the universe feel less like chaos and more like composition. Every star contributes to that structure. Each one is born from the collapse of a cloud of gas and dust, spinning faster as it condenses, heating until fusion begins. In those first moments, hydrogen atoms begin to merge into helium, releasing energy that radiates outward. That radiation pushes against gravity, creating a balance that can last for billions of years. Around those newborn stars, leftover material forms disks that gradually coalesce into planets, moons, and asteroids. The process repeats across the galaxy, billions of times over, creating systems within systems. If you could see it from outside space and time, you'd see waves of creation rippling outward, stars forming in clusters, then drifting apart, leaving trails of light in their wake. Each generation of stars adds something new to the composition. The first stars, massive and short-lived, produced the heavier elements that later stars would inherit. When they exploded as supernovae, they scattered carbon, oxygen, iron, and all the other materials necessary for planets and life. Those elements mixed with gas clouds, forming the raw ingredients for the next generation. Our sun carries that legacy. Every atom of iron in your blood, every molecule of oxygen in your breath, every grain of calcium in your bones was forged inside a star that lived and died long before the sun existed. In that sense, we're part of a continuous sequence of creation. Not spectators, but products of the same process. When scientists talk about stellar populations, they categorize them by age and composition. The oldest metal-poor stars that formed early in the galaxy's history, and the younger, metal-rich ones like our Sun. The younger stars tend to have more complex planetary systems, because they were born from material enriched by generations of earlier stars. That enrichment is what makes planets like Earth possible. Without the heavy elements created in ancient supernovae, there would be no solid ground, no air, no life. The galaxy, in that sense, builds complexity through repetition. Every cycle of star birth and death adds new notes to the pattern. Planets, too, contribute to that rhythm. They orbit in resonances, patterns of motion that stabilize their systems. Jupiter's moons, for example, follow a precise relationship. For every orbit of Europa, Io completes 2, and Ganymede completes 1 for every 2 of Europas. These gravitational patterns prevent collisions and create tidal forces that generate heat, shaping the environments of the moons. Similar resonances exist in exoplanet systems, forming repeating ratios that give the orbits a kind of mathematical rhythm. The entire galaxy is full of these relationships, interactions that seem almost musical in their regularity, not by design but by the natural outcome of gravity and motion. Even light itself behaves rhythmically. Stars pulse, some slowly, others in rapid beats measured in seconds. Their brightness rises and falls in patterns determined by their internal structure. Cepheid variables, for instance, expand and contract in a steady rhythm that allows astronomers to measure distance by timing their pulses. The universe speaks in oscillations, from the vibration of atoms to the rotation of galaxies. If you could somehow translate those frequencies into sound, the cosmos would hum with an endless shifting tone. The Milky Way, our home galaxy, rotates too, though so slowly we can't feel it. It completes 1 revolution every 200 million years. During that time, stars move in and out of its spiral arms, where new stars are born in dense clouds of gas. The spiral structure itself is a kind of standing wave, a pattern that persists even as individual stars move through it. Each arm is not a fixed object, but a region of activity, like the crest of a wave that passes through water without the water itself travelling far. On a galactic scale, even that motion becomes part of a greater rhythm, a pattern that connects stars, planets, and the vast regions between them. Life, when it emerges, becomes another form of rhythm layered atop the physical one. It takes the steady pulses of light and temperature from its parent star and turns them into cycles of growth and rest. On Earth, those rhythms define everything. The rotation of the planet creates day and night. Its orbit creates seasons. The tilt of its axis creates variation in light and temperature. Living things have evolved to match those cycles. Photosynthesis by day, rest by night, migrations, hibernations, and reproductive seasons. Every organism participates in this exchange between energy and environment, keeping time with its world. If life exists elsewhere, it too would be shaped by the rhythms of its planet and star. A world orbiting a red dwarf might experience long, slow days and nights, with light that never turns white but stays in shades of orange and crimson. The organisms there might evolve pigments suited to that dim light, absorbing energy differently than plants on Earth. A tidally locked planet might have perpetual daylight on one side and eternal darkness on the other, creating a world divided between heat and cold. Life might cluster in the twilight band between them, adapting to constant half-light. The forms it takes would reflect the balance of forces that define its home: gravity, light, chemistry, and time. What's remarkable is how consistent the underlying principles seem to be. Everywhere we look, from the smallest cell to the largest star, we find systems maintaining equilibrium through cycles: feedback, adaptation, oscillation. The universe seems to favour patterns that endure through repetition. That doesn't mean it's intentional or purposeful. It's simply the nature of stability. Systems that oscillate survive longer than those that remain static. Change keeps balance alive. The same holds true for our own planet. The climate cycles, the carbon cycles, the circulation of air and water, all are forms of rhythm. The Earth breathes through these systems, not metaphorically, but literally, exchanging gases between the biosphere, atmosphere, and oceans in repeating patterns. When those rhythms are disrupted, the system seeks a new equilibrium. Sometimes that adjustment is gentle, sometimes it's catastrophic. But always the drive toward balance persists. From a human perspective, it's easy to see this as fragile. We experience the consequences of imbalance, drought, flood, heat and cold, and interpret them as deviations from normalcy. But on a larger scale, those fluctuations are part of the pattern. The universe doesn't draw moral lines between creation and destruction. Both are part of the same ongoing process. Stars die so that new ones can form. Planets change so that new conditions can arise. Life evolves through extinction as much as through survival. What feels tragic to us is, on a cosmic scale, continuity. When we speak of a symphony of the stars, it's not to romanticize but to recognize that the cosmos operates in layers of interlocking processes, each one influencing the others. Energy moves from one form to another, from fusion to light, from light to chemistry, from chemistry to thought, and then back again. Every life form, every planet, every burst of radiation contributes to that flow. The result isn't music in the emotional sense, but structure, coherence, and persistence. It's humbling to realize that our own bodies are part of that same exchange. The calcium in our bones once resided in the core of a star. The carbon that fuels our cells was once part of a molecule drifting through interstellar space. The oxygen we breathe was formed in nuclear reactions that occurred billions of years ago. When we exhale, we return some of that matter to the atmosphere, where it will be taken up by plants, dissolved in oceans, and eventually cycled back into rock. The process never stops. Matter moves through forms. Energy drives the movement. The symphony plays on whether we notice or not. Even the light that reaches Earth participates in that continuity. Photons from the sun scatter in the air, bounce off surfaces, and eventually dissipate as heat. A fraction of them leave the planet entirely, carrying information about Earth's composition into space. In that sense, we are not separate from the rest of the galaxy. We're part of its conversation, adding our own faint signals to the background. The light that escapes from Earth joins the collective radiance of the Milky Way, becoming indistinguishable from the glow of countless other worlds. That thought can feel isolating, but it's also grounding. It means we are part of something enormous, connected through the most fundamental forces of nature. Every particle of light, every vibration, every orbit participates in the same physical laws. The galaxy may seem silent, but in the silence there is motion, interaction, balance, the steady persistence of processes that have been unfolding since the beginning of time. If we could compress the history of the universe into a single hour, the formation of Earth would happen in the last few minutes, life in the final seconds, and human civilization in a fraction of a heartbeat. Yet even in that brief instant, we've begun to add our own patterns to the larger one. Cities glowing at night, radio waves radiating outward, satellites orbiting in predictable paths. In the cosmic scale, those additions are tiny, but they exist, woven into the broader structure. We've become participants in the rhythm, conscious instruments in the symphony, aware of the notes we're playing even if we can't hear the whole composition. That awareness is what makes our perspective unique. The stars don't know they're part of a pattern. We do. We can observe, analyze, and reflect. We can see how the same laws that shape galaxies also govern the behavior of atoms. We can trace the connections between motion and energy, between structure and time. Our ability to perceive those connections doesn't make us central to the universe, but it makes us witnesses to it, observers who can translate the physical into meaning. As we study other worlds, as we listen for signals or measure atmospheres, what we're really doing is learning to recognize more layers of that pattern. Each discovery adds texture, a new rhythm, a new relationship. We see how planets orbit in harmony, how stars pulse, how galaxies collide and merge. We begin to understand that the cosmos isn't random, even if it isn't directed. It's structured through feedback, through interaction, through the persistence of energy finding balance in motion. And that realization changes how we think about life. If everything participates in the same pattern, then life isn't an interruption in the universe's flow. It's a continuation of it. Chemistry becoming complexity is as natural as gas becoming a star. The processes that sustain us are the same ones that sustain the stars themselves: fusion, radiation, motion, equilibrium. The universe doesn't separate living from non-living as clearly as we do. It builds both from the same rules. To see the universe this way is to find peace in its scale. We no longer need to imagine it as empty or lonely. It's full, not necessarily of voices or civilizations, but of patterns, cycles, and relationships. The stars may not sing, but they resonate. Their gravity shapes space. Their light shapes time. The planets that orbit them carry traces of that influence, each contributing to the balance of forces that keeps everything moving. The result is something vast, continuous, and self-sustaining. Not a song we can hear, but one we can recognize in motion and change. When you look at the Milky Way on a clear night, stretching across the darkness as a pale band of light, it's easy to forget what you're actually seeing. Every shimmer is a star, and around almost every star there are planets. That means the sky you see is not just filled with stars, it's filled with worlds. Some are small and rocky, others are vast and gaseous, some orbit close to their suns, others drift in the cold outskirts. Together they form a population so immense that it's difficult to comprehend. There are at least 100 billion stars in our galaxy, and the number of planets is likely even greater. If even a small fraction of those planets can host life, the Milky Way might be full of possibilities. For a long time, we didn't know that. We suspected, we guessed, we hoped, but we didn't have proof. That changed in the early years of this century when technology finally allowed astronomers to detect planets orbiting distant stars. What began as a few isolated discoveries has turned into an ongoing flood of confirmation. Today, we know of thousands of exoplanets, and we've only surveyed a tiny portion of the sky. That means what we've found so far is just a fraction of what's out there. If you multiply the average number of planets per star by the number of stars in the Milky Way, the result is staggering. Hundreds of billions of worlds, each one with its own conditions, its own history, its own potential. Some of these planets resemble Earth in size and temperature. Others defy comparison. We've found worlds that orbit two stars, worlds covered entirely in water, worlds with atmospheres thicker than Venus's, and others so thin they barely exist. There are planets so close to their stars that they're tidally locked, with one side in perpetual day and the other in endless night. There are gas giants orbiting farther from their stars than Pluto does from the Sun. There are planets that drift freely between stars, unbound, wandering through interstellar space after being ejected from their systems. The diversity is immense, and the more we find, the more we realize how varied planetary systems can be. What makes this variety so meaningful is that it gives us context. For most of human history, Earth was our only example of a planet, our only reference for what a world could be. Now, with every new discovery, we learn more about the range of possibilities, the different ways that matter, gravity, and energy can combine to create stable environments. Some of these environments might seem hostile by our standards, but nature has a way of using every available niche. If life can adapt to the boiling vents of Earth's oceans or the frozen deserts of Antarctica, it's not unreasonable to think it could adapt elsewhere too. The most promising candidates for habitability are the small, rocky planets that orbit within their stars' habitable zones. the regions where temperatures allow liquid water to exist on the surface. Astronomers have already identified several such planets, including ones in nearby systems like Proxima Centauri and TRAPPIST-1. The TRAPPIST-1 system, in particular, is remarkable. It has 7 Earth-sized planets, 3 of which lie in the habitable zone. They orbit a small, cool red dwarf star just 40 light-years away. If you could stand on one of those planets, the others would be visible in the sky, appearing larger than our moon does from Earth. Whether any of them actually support life is still unknown, but their existence alone shows that Earth-like conditions are not unique. Red dwarfs like TRAPPIST-1 are the most common type of star in the galaxy. They burn slowly and can last for trillions of years, far longer than the Sun. That longevity makes them intriguing targets in the search for life. If life can survive the flares and variable light of these stars, it might have an enormous amount of time to evolve and adapt. Some scientists think that most habitable planets in the Milky Way could orbit red dwarfs, simply because there are so many of them. If that's true, then the galaxy's most likely homes for life might not resemble our Sun's neighbourhood at all. They might be dimmer, redder, quieter places where life unfolds slowly under a cooler light. But the search doesn't end with individual stars. Astronomers also study the structure of the Milky Way itself, where in the galaxy life is most likely to thrive. The inner regions closer to the galactic core are rich in heavy elements, the building blocks of planets. But they're also dangerous. Supernovae and radiation bursts are more common there, and such events can sterilize nearby systems. The outer regions, by contrast, are calmer, but have fewer of the elements needed to form rocky worlds. Somewhere in between lies what scientists call the galactic habitable zone, a region not too close to the core, not too far from it, with a balance of materials and safety. Our Sun happens to reside within that zone, about halfway between the centre and the edge of the galaxy. Whether that's coincidence or inevitability is hard to say, but it's another reminder of how finely tuned our circumstances are. Even with those ideal conditions, the odds of life developing on any given planet remain uncertain. We still don't know how often chemistry turns into biology, but the fact that we've found so many potentially habitable worlds so quickly suggests that the ingredients are widespread. The molecules necessary for life, water, carbon compounds, amino acids, have been detected in interstellar clouds, in comets, and in the atmospheres of exoplanets. Life's chemistry seems to be written into the galaxy itself. It's not confined to one world or one set of conditions. The idea that life might be common changes how we see the Milky Way. It transforms it from a static backdrop into a living network of possibilities. Each star could be the centre of its own story, each planet a stage for chemistry, weather, and evolution. Some may be barren, others vibrant, some already gone, others just beginning. The galaxy becomes a vast laboratory with billions of experiments running simultaneously, each one shaped by gravity and time. Our ability to study those worlds is improving rapidly. The James Webb Space Telescope and other observatories are beginning to analyse the atmospheres of exoplanets directly, searching for biosignatures, gases like oxygen, methane or ozone that could indicate biological activity. The first confirmed detection of such a signature would be one of the most significant discoveries in history. It wouldn't necessarily prove the existence of life, but it would show that the conditions for it exist elsewhere. That single piece of evidence would shift our perspective permanently, turning the idea of possibility into something closer to probability. Even without direct evidence, the sheer scale of the galaxy makes isolation seem unlikely. If the Milky Way contains around 100 billion stars, and if just 1% of them have habitable planets, that's still a billion potential worlds where life could arise. If even a fraction of those worlds develop intelligent life, then there could be millions of civilizations scattered across time and space. The numbers are vast enough that even conservative estimates lead to dizzying possibilities. Yet for now, the silence remains, a reminder that probability doesn't guarantee contact. The distances between stars are enormous, and that distance alone creates isolation. Even light, the fastest thing in the universe, takes years to travel from one star to another. Communication between civilizations would require patience beyond what we can easily imagine. It's possible that signals are travelling right now, but they haven't reached us yet, or that they passed long before our species appeared. The galaxy could be full of messages that have come and gone, echoes fading into the background radiation. Still, the thought of so many potential worlds is comforting. It means the conditions that support life are not rare. It means that what happened here could happen again elsewhere, perhaps many times over. Even if we never meet another civilization, knowing that life might be widespread gives the universe a different character. It turns the night sky from a void into a community, not of people or voices, but of possibilities, each one carrying its own version of the same story: matter, organising, adapting, enduring. The search for habitable planets isn't just about finding another place to live, it's about understanding the context of our own existence. Every new discovery helps us see Earth more clearly, showing what makes it ordinary and what makes it extraordinary. It reveals that the same processes that shaped our world are happening all over the galaxy. Planets form from disks of dust, atmospheres evolve, climates stabilise or collapse. Life, if it arises, must navigate those same challenges. We're not separate from that pattern, we're one example of it. It's easy to imagine that somewhere, on a world orbiting a distant star, there could be oceans under alien skies, forests of unfamiliar colours, creatures shaped by gravity and light in ways we can't picture. Perhaps their nights are lit by multiple moons, or their days are longer than ours, stretching endlessly under a pale sun. Each variation adds another note to the galaxy's diversity. What seems exotic to us would be normal to them, just as our blue skies and green landscapes would seem extraordinary to anyone accustomed to a different kind of light. In thinking about these possibilities, we also begin to sense the scale of time involved. Civilizations, if they exist, might rise and fall across millions of years. Their entire histories could pass unnoticed from our perspective. The galaxy's age is vast enough to accommodate countless beginnings and endings. The fact that we haven't yet detected others doesn't mean they never existed. It might just mean that our moment doesn't overlap with theirs. The Milky Way itself is not static. It moves, evolves, and interacts with its surroundings. In a few billion years it will merge with the Andromeda Galaxy, creating a new, larger structure. Stars will be rearranged, planets displaced, orbits altered. The possibilities that exist now will change, but new ones will emerge. Even on that scale, the process continues: creation, destruction, reformation. The galaxy is a living system, not alive in the biological sense, but dynamic, constantly changing. When astronomers map its structure, they see spiral arms filled with regions of star formation, where clouds of gas and dust glow with the light of new suns. Those regions are like nurseries, places where the next generation of possibilities is being prepared. Each of those stars will one day host planets, and some of those planets will fall within their stars' habitable zones. Even if most of them remain sterile, the sheer number ensures that some will not. The galaxy's scale makes possibility inevitable. For all the progress we've made, we're still only beginning to explore. Our telescopes can barely resolve the smallest details of nearby systems. The light we study from distant planets often consists of only a few photons captured after travelling for decades or centuries. Yet from those faint signals, we can infer so much. Temperature, composition, motion, even the presence of clouds or weather. It's astonishing that from a single beam of light, we can reconstruct the nature of a world hundreds of trillions of kilometres away. The more we learn, the more connected everything seems. The galaxy isn't a collection of isolated points, but a network of influence. Gravity linking stars, radiation linking systems, light carrying information across vast distances. The same processes that formed Earth are still happening elsewhere. Every time a new star ignites, every time a planet cools and solidifies, another potential home for life appears. The galaxy renews itself endlessly, maintaining a balance between creation and decay. When you think about it that way, the odds of life being unique to Earth start to feel smaller and smaller. It may not look like us or think like us, but life in some form, microbial, plant-like, or something completely different, could be widespread. It could exist beneath ice, within clouds, or in oceans of substances we'd find toxic. Life might not be rare. It might be the natural outcome of chemistry given enough time and stability. We may never see those worlds up close, but that doesn't make them less real. Their light reaches us, their existence measurable in the faintest dips and shifts of starlight. Every confirmed planet adds one more piece to the puzzle, one more reminder that the galaxy is active, filled with potential, far from empty. We're surrounded by possibilities so numerous that our minds can't hold them all at once, and as that realization sinks in, as the thought of billions of unseen worlds settles quietly in the mind, a new kind of perspective begins to form. We start to see ourselves not as the centre of anything, but as part of a vast ongoing pattern, a single moment in a galaxy full of moments. Every life, every world, every particle participates in that shared existence. It's a thought that feels both expansive and grounding, immense yet intimate. Somewhere out there, beyond the reach of our instruments, there may be other beings looking up at their own skies, asking the same questions, wondering if they're alone. Perhaps their technology isn't advanced enough to detect us, or perhaps they too are surrounded by silence. But the possibility of their existence is enough to remind us that we share something profound, the same galaxy, the same physics, the same curiosity. And as that quiet recognition unfolds, it begins to lead naturally toward reflection. Because amid all these worlds, all this potential, one still stands out to us. Not because it's better, but because it's ours. The Earth, fragile and improbable, drifting through a galaxy of possibilities, remains the only place we've ever known where the question of life has already been answered. You are here, on one small world in a galaxy of possibilities. The air around you, the ground beneath you, the faint hum of everything alive, are all connected to the same processes that shape stars and planets. It can be easy to forget that. Daily life happens on a scale so narrow, measured in minutes and meters, that the larger story fades into the background. But every breath you take, every sound you hear, every particle in your body belongs to that wider story. You're not separate from the universe. You're one of its ways of looking at itself. The light that reaches your eyes when you look at the night sky is ancient. Some of it began its journey before your species existed, before the first humans looked upward and gave names to the stars. That light has crossed unimaginable distances, passed through dust and gas, through the pull of gravity, through the quiet persistence of time, just to arrive here, now. It carries information about the past, about what was, but it also connects you to the present. You are seeing not just what was, but what endures. In a galaxy full of motion and change, the fact that light still finds its way to you is a small but remarkable continuity. Sometimes when people talk about space, they describe it as empty. But that's never really true. The space around you is filled with fields and particles, radiation and dust, echoes of ancient events. Even the space between atoms is not truly empty. It's full of potential, of movement, of quiet energy. The universe doesn't stop at the edge of the sky. It continues through you, through the air, through the spaces between your thoughts. Every part of it is connected by the same physical laws, the same materials, the same unfolding. When you think about everything that had to happen for this moment to exist, it becomes almost overwhelming. The formation of stars, the creation of elements, the birth of planets, the evolution of life, the emergence of consciousness. Each step took billions of years. Each depended on countless coincidences and balances. And yet, somehow, all of it led to now. Not in the sense of destiny, but in the sense of continuity. The present isn't separate from the past. It's built from it, shaped by it, carried forward by everything that came before. You, sitting or lying wherever you are part of that sequence. Your body is made of atoms forged in stars. The water in your cells has been part of oceans and clouds, part of the air, part of other living things. The calcium in your bones, the iron in your blood, the oxygen in your breath. All of it has been elsewhere before, and all of it will be elsewhere again. The universe doesn't waste material, it recycles endlessly. You're one temporary arrangement of those materials, one configuration of energy and matter that, for a brief time, is aware of itself. It's difficult to hold the scale of that idea in your mind. The Milky Way alone spans 100,000 light-years. Beyond it, there are hundreds of billions of other galaxies, each with its own collection of stars and worlds. Yet from your perspective, all of that fits into a single sky. The immensity of it doesn't cancel out your smallness. It includes you in it. You're as much a part of the universe as the stars are. The same laws that govern their fusion govern the beating of your heart. The same particles that drift through interstellar space drift through you. When you close your eyes, the universe doesn't go away. Its motion continues, quietly, constantly. The Earth rotates, the moon orbits, the galaxy turns, light travels, gravity pulls. You are in motion even when you feel still. You're part of a planet moving through space at 30 kilometers per second, orbiting a star that itself moves around the galactic center. Everything around you, even the most solid object, is made of motion on a scale too small to see. Atoms vibrating, electrons shifting, energy passing from one state to another. Stillness, in that sense, is only relative. Beneath the surface, everything is dynamic. To exist here, now, is to be at the intersection of countless processes, biological, chemical, geological, cosmic. The warmth of your skin comes partly from sunlight that left the sun 8 minutes ago, and partly from the energy stored in the molecules of food you've consumed, which themselves are the result of sunlight captured by plants. Every thought you have requires that energy to flow through neurons, each signal depending on the same electrochemical principles that govern lightning and stars. Awareness, at its most basic level, is physics in motion. The same is true for the sensations you experience as you listen to these words. The air vibrates, carrying sound waves that reach your ears, where they're transformed into electrical signals, then interpreted by your brain as language, as meaning. What feels like communication is, at its core, the exchange of energy across distance. It's not so different from how light travels between stars, how gravity links worlds, how information moves through the galaxy. Every act of perception is a miniature version of that same process. Connection through interaction. It's strange how easily we forget that this is extraordinary. Because we live inside it, the miracle becomes normal. We think of the world as background, as something that just is, rather than something that's constantly being sustained by a balance of forces. The atmosphere doesn't just sit in place, it's held by gravity, warmed by sunlight, circulated by the planet's spin. The oceans don't simply exist, they form, evaporate, fall and form again. The soil that grows food is the product of erosion, decay and time. Every stable thing is maintained by instability beneath it. The surface calm of your daily experience hides a constant negotiation between opposing forces. When you think about that, it becomes clear that fragility and stability aren't opposites. They depend on each other. Earth is stable because it's dynamic. Its systems remain balanced only because they keep changing. Life, too, survives through adaptation, through continual adjustment to new conditions. You are part of that process. Your body maintains homeostasis, balance through change in every cell, every heartbeat, every breath. The same pattern that governs the climate and the orbit of planets governs your metabolism. You're a reflection of the universe's way of keeping balance. That connection extends beyond biology. The human ability to imagine, to understand, to seek patterns is part of the same tendency toward coherence. When you wonder about the stars, when you ask how many worlds might exist or what life might look like elsewhere, you're participating in the universe's own curiosity. The act of asking those questions is a continuation of the same process that created the stars themselves. Energy organizing into form, form organizing into thought. Consciousness isn't an exception to the universe, it's one of its outcomes. The more we learn about the cosmos, the more we realize that it doesn't need to be kind or purposeful to be meaningful. Meaning doesn't come from the universe having a plan, it comes from our awareness of being part of it. The universe exists whether or not anyone observes it, but observation turns existence into experience. To know that you are made of the same elements as the stars, that your thoughts are powered by the same physics that fuels the sun, is enough to make belonging real. You don't need more than that. It's easy, especially in quiet moments, to feel small when you think about the size of the galaxy. But smallness doesn't mean insignificance. In a system this large, everything matters because everything contributes. A single grain of dust can seed a star. A single planet can host life. A single mind can ask a question that changes understanding. The scale of the universe doesn't diminish you. It contextualizes you. It shows that being small is the natural state of things. Every large structure is made of smaller ones, each dependent on the rest. If you could step outside of time and watch the Milky Way unfold, you'd see a slow choreography. Stars forming, drifting, dying, their remains forming new stars. You'd see clouds collapsing into planets, collisions creating moons, gravity shaping everything into spirals and clusters. Somewhere in that slow motion, you'd see one small planet where chemistry became life and life became aware. The fact that you can think about that sequence at all means you're already part of it. The story is not happening to you. It's happening through you. Every person alive is connected by that shared origin. The differences between us, language, culture, circumstance, are surface details. Underneath, we're all products of the same long history, made from the same matter, shaped by the same forces. Even your thoughts about distance and difference are made possible by atoms that were once part of stars that exploded billions of years ago. When you consider that, the boundaries between self and universe begin to feel less rigid. What separates you from the stars is not essence, but scale. The light that left Earth tonight will continue outward forever, spreading thinner as it travels, but never truly disappearing. It will become part of the faint glow that fills the galaxy, blending with the light from every other world. In that sense, you are not just part of the universe's history. You are part of its expression. The energy that sustains you now will eventually return to that larger circulation. Nothing is lost. It only changes form. That's as true for matter as it is for moments. The experiences you have now, the thoughts, the emotions, the awareness, are temporary configurations of energy. They arise, move through you, and dissipate, but the process that allows them continues. If you let that thought settle, there's a kind of quiet comfort in it. The awareness that you exist in this moment, that you're surrounded by stability built on change, that you're connected to everything else that has ever been, can bring a sense of calm. The world can feel chaotic and uncertain, but underneath it the same physics continues, unbroken. Stars still form, planets still orbit, light still travels. The same balance that shaped the galaxy is at work in you. You don't need to solve the scale of it. You don't need to find an answer to why you exist. It's enough to recognize that you do. Here, now, in this brief interval of awareness between past and future. The galaxy continues regardless, and yet, for this moment, you are aware of it. You can think about it, imagine it, feel connected to it. That, in itself, is remarkable. You are one of the ways the universe knows it exists. As time passes, your thoughts, your body, and everything around you will change, as they always have. The atoms that make you will eventually become part of other systems, part of air, part of rock, part of other living things. The continuity will go on. The same patterns will repeat in new forms. You're temporary, but you are part of something permanent. And as that realization takes hold, it becomes easier to breathe, to rest, to let the constant background noise of thought quiet down. The universe isn't demanding anything from you. It isn't asking for belief or achievement. It's simply continuing, and you are part of its continuation. The same forces that shape galaxies are at work in your heartbeat, your breath, your awareness of this very moment. The Milky Way will keep turning, stars will be born and die, planets will form and dissolve. Life, in one form or another, will continue to search, to adapt, to observe. And through it all, there will always be moments like this. Small, quiet intersections of consciousness and time, where a being on a small world looks up and feels the weight and the wonder of belonging. You are that being now, and in this instant, the entire history of the universe leads here, through you, through this awareness, through this simple truth. You exist, here, now.